All right. Good morning, everyone. This is Pete Bernard, CEO of the EDGE AI Foundation. I'm here with Petrut Bogdan. Petrut, do you want to introduce yourself as well?
Sure. I generally go by Peter, so very nice afternoon from across the pond. I'm Peter. I'm neuromorphic architect at Inatera and chair of the neuromorphic working group of the foundation.
Yes, this is our first neuromorphic live stream event that's happening, which is pretty cool. So I'm actually dialing in from Bellevue, Washington. So it's a nice and early morning for me. It's late afternoon for you.
I'm dialing in from The Hague in the Netherlands.
Excellent. We have a lot of people on the chat. So one of the things, if you want to say where you're dialing in from on the chat, that would be fantastic. I see we've got, I think we've had like 400 or 500 people registered for this thing. We're on YouTube, we're on Twitch, we're on LinkedIn. So definitely join in. This is going to be an interactive conversation we have today with some of the leading thinkers in the space, and part of the deal is you get to ask questions with some of the experts here. So yeah, there you go. Hamburg, Cork, UK, Brussels, Athens, Paris, Iran. Let's see, keep going. Dallas, Texas, Innsbruck, Austria, Munich, Hyderabad. Let's see, where else? Melbourne, okay. Belgium, let's see. Keep going. Anyone from New Jersey? I'm just kidding. I'm from New Jersey. Petru, why don't you kind of, before we get into the speakers, can you give us, from your many, many years of experience and study, like how do you define neuromorphic computing, and how is it differentiated from a lot of the stuff that's happening out there today?
So this has always been a difficult question, and it will continue to be a difficult and contentious question. Nope, you started off with the big guns. There's been relatively recently, there's been quite a bit of debate in the academic community about whether the term neuromorphic is overloaded or not, and whether it still has the same meaning that it did 30 years ago or so. Yeah. Generally, so I come from an academic background. I used to work on Spinnaker, a very 1 million ARM core supercomputer for simulating brains. And whenever we were having conversations or educating youngsters, folk, policymakers, we were talking about brain inspiration. So neuromorphic is brain-inspired compute, but now brain inspiration can come in many different ways. It means different things to different people. For some folk, it means analog compute with spikes. So you emulate neurons and synapses from the brain into a physical substrate. It's evolved quite a bit since then. So I think we're going to see today quite a few different interpretations of what neuromorphic is, what neuromorphic can be, from the definition of maybe analog mixed signal with spikes to in-memory compute, to alternatives that are much more traditional but focus on event-based computation and representations. So doing a lot of work with exploiting either sparsity of weights or sparsity of activations. So I think we're going to see quite a few visions of what neuromorphic could be today. And I think most importantly, the way that it differs, that I feel that it differs in a few different ways from traditional approaches, but generally some of the features that you'll see is exploitation of sparsity in some way, event-driven computation in some way. So basically not waiting for all computation to finish in one layer of a neural network before continuing on with the next. Massively parallel architectures, so being able to sort of similar to how a GPU would do it, but with probably much more heterogeneous workloads per core. Quite a few features that make neuromorphic different as an architecture, as a paradigm, as a way of thinking about neural networks.
Yeah. No, I think we'll definitely hear a kind of an interesting diversity of perspectives on that today. One of the ways I describe it to folks, kind of cocktail party level discussion, is I mean, part of the title of this is, beyond von Neumann compute. So, what we've been doing so far pretty much has been writing AI code to sort of fit into traditional hardware architectures, right? The von Neumann architectures, which have been around for decades. But a lot of what I see in the neuromorphic space is, what if we re-architected the hardware and the semiconductors and the platform around the AI, the optimal AI models, as opposed to trying to jam AI models into a traditional architecture. So that's another way of thinking about it, is it's really kind of turning things on its head, or flipping the script, as we say in the US, to sort of really figure out optimization and incredible efficiencies and power and performance. So that's what we're in for today. We have a pretty big agenda. Before we get into it, let me do a little public service announcement. EDGE AI Foundation. Peter is the chair of the working group for neuromorphic. We have seven or eight working groups. We're actually the world's largest community of EDGE AI developers, tech makers, and academia. We operate worldwide. We're underwritten by about 60 or so tech companies, everyone you've heard of, and a bunch of folks you probably haven't heard of yet. We work with a bunch of universities as well, big scholarship fund. So that's what we're all about. And you can go to edgeaifoundation.org, learn more and engage. One of the things we also do, we do events. We show up at events, we'll be at Embedded World, things like that, but we do our own events too. We have one in San Diego that's coming up. And I'll show you that. It's March 24th to the 26th in San Diego. If you scan that QR code, or go to San Diego 2026.edgeaifoundation.org, you can sign up and join us there. 3 days of talks and demos and workshops. I think about 15 hours of hands-on workshops. Really good panel discussions. You'll hear from professors from UCSD, UC Riverside, Intel, Qualcomm, the U.S. Navy, missing somebody, DeepX. It's going to be lots of fun. So come down to San Diego if you can. I see a few folks on the chat. Someone's from LA, so you have no excuse to come and join us there. So we do those things, and we do this really just to kind of, we're a nonprofit. We're here to kind of educate folks and empower people with knowledge, and that's why we do these kind of live streams. And as you can tell, we're pretty excited about neuromorphic computing, and the working group has done some amazing work here to do that. So that is my PSA. Another PSA is the launch of the Thor initiative, which is happening on Monday at UT San Antonio, and I will be there in person. And that's another initiative that we're connected to, and you're going to see lots of cool things out of the Thor initiative at UT San Antonio. And you can go Google that and find out more. Let's see what else. What's the agenda look like today, Peter? Just to give people a little preview before we jump into it. What's the preview?
So today we're joined by 5 experts and myself. So we are going to have 6 presentations talking about different levels and different deployments of neuromorphics. We've tried, so this first inaugural online conference is an invitational, and we've selected quite I feel a good range, a fantastic range of people to talk to us about large scale, medium scale, small scale neuromorphic deployments from an industrial perspective and from academia. So we're gonna start off. Do I announce who we start off with, or is it?
Well, why don't you just run through the quick agenda for everybody, so then we can. By the way, this is all going to be recorded on YouTube after this too. So if you need to take a little pee break or a coffee break or work break, go for it. We'll still be here. Don't worry about it. But yeah, can you give us like a little heads up? Who's who in the zoo on this one?
Who's who? Okay, so we're going to have 6 presentations. We're going to be started off by Hector Gonzalez, who's the CEO of SpinCloud, a company based in Dresden. And they're working on a platform called, well, I think the chip and maybe also the platform, but Hector can tell me if I'm wrong, are called Spinnaker 2. I expect, because we had this issue with Spinnaker 1 where it was ambiguous whether Spinnaker meant was referring to the chip, the software, the platform. It's a spiking neural network architecture is what we're going for. So talking about some of their
coffee creamer, it's all that stuff.
Sorry,
go ahead.
Mike closer.
Mike, okay, keep going, please.
Okay, and then we're going to be joined by Matthew Yadutenko, who's a postdoc at TU Delft. He's going to talk about exploiting biological priors for event-based motion estimation.
Nice.
His lab has, their lab has done some amazing work also on drone control, and they've shown very impressive results there. So we're trying to focus on what is the neuromorphic perspective in the physical AI space, which is now booming in terms of interest. We have Jonathan Tapson, who is CDO at BrainChip, who's going to show their perspective on what is neuromorphics and probably their Akida platform and future and philosophical perspectives as well on neuromorphics. Then we were meant to be joined by one of my colleagues, but he couldn't make it. So I am going to be giving a presentation instead from Inatera, a scale-up startup based in the Netherlands, talking about vertically integrated neuromorphics. So I'm going to talk about our chip, our microcontroller that has SNNs in it, used for radar applications. Then we're going to Harvard, going back across the pond on your side of the aisle, to talk to Jason Yeek, who's a PhD student there, who's going to be talking to us about optimizing neural networks for neuromorphic accelerator deployment. Jason has done fantastic work in the past with coordinating a very large-scale benchmarking activity in the neuromorphic space called NeuroBench. Then we're going to UCSC, to Santa Clara, to Jason Eshragian, who's an associate professor there, and he's going to end the, last but not least, ending the conference with talking about neuromorphic LLMs, which I think are of great interest to the community, EDGE AI, and more widely the AI community.
Yeah.
So that's kind of it. That's kind of the schedule for today.
Well, let's get into it. Just to let everyone know, as I mentioned, this will be on YouTube. The agenda should be in the YouTube description, and it should be on StreamYard description and stuff like that. If you're on Twitch, you don't see the agenda, I'm sorry. But that's Twitch for you. So let's kind of bring on our first person, and then I will fade it at the background. But let's bring on Hector. Okay.
Hector, hello.
Let's bring you into the guest spot here. And you have some slides to share, I think, right?
Yeah. Yeah, thank you so much for the invitation. I can jump straight into it.
Let's see, where are the slides? Are you sharing a screen right now? Oh, there it is.
Is it?
Boom. Okay. I will exit out. Peter, you can stay if you'd like. I'm going to go get a cup of coffee. The floor is yours.
Why would anyone want to see my face? Let's leave Hector to it, and then we can come back with the questions.
Very iconic face, you can say the truth. Yeah, thank you so much for the invitation. I mean, I will be talking, funny enough, not about small stuff, like basically edge devices, but more around data center scale. But the perspective that I'm bringing into the presentation is rather, how can these brain-inspired concepts and how can this dynamic sparse principles actually be used at a data center scale, and also how these principles within data centers for state-of-the-art AI models are kind of shaping an important overlap with where all the mainstream AI models are going. So that's kind of it's not intended to go into a very detailed presentation, but it's more to give a top-level overview on how to bring this brain inspiration to data centers and how this overlaps with this state-of-the-art AI model. So yes, it was already kindly introduced. My name is Hector. I am one of the founders of SpinCloud, and I am leading the company there. And I would basically walk you through a few of the things and systems we have built. So I mean, the very first step, or let's say the very first motivation that I think with everyone designing brain-inspired systems of neuromorphic systems, or however you want to call them, it's basically there's always the motivation of trying to get closer to the efficiencies of biological brains. So, I mean, the human brain is one of the most advanced supercomputers in the universe, if not the most. I mean, it can do things that artificial intelligence today can still only dream of. I mean, we're getting close to many interesting stuff, but still the efficiency gaps that are between biological systems and artificial systems remains huge. I mean, the brain only consumes about 20 watts and really can do things that are super interesting today. So then looking ahead, let's say looking at brain inspiration, like there is that term that basically encapsulates neuromorphic, which basically implies what really what are key principles that we should copy from the brain? So as Petrut was already introducing at the beginning, so it is like quite a wide spectrum, and for different people, it means different things. But if you think about it, essentially what people are doing, trying to copy things from the brain is really what this picture kind of encapsulates. So you're looking from the outside, you're looking how brains operate, and you're trying to copy things that you think are interesting and relevant and that are contributing to the efficiency of biological brains, but you don't know for sure because essentially the brain is still like kind of an active field of research. So you're trying to copy these different characteristics to design systems that are more efficient. Along these lines, there is a huge spectrum. I mean, Petrut already like kind of mentioned different levels of abstraction. So basically I have encapsulated like kind of different abstraction levels depending on how much systems are highly inspired or committed to biological inspiration. So essentially systems that are sitting at the very bottom of this curve are very efficient at running spiking neural networks. So they are very, very committed to biology. They are very committed to spikes from a device levels perspective. So you have, for example, here people working on memristor devices. You're also working on optical-based neurons. You're kind of people that are very close to the device. If you go slightly up, you find people that are using analog compute principles to encode this brain dynamics. If you go slightly up, you have people that have a combination like analog mixed signal. Then here you have people that are encoding this brain dynamics into the digital substrate, into what's known into chip design like RTL. And here they're having a little bit some initiatives basically in the FPGA space, particularly in Australia, about how to emulate using off-the-shelf hardware that is programmable and configurable. And we sit at a level where we are the least committed to spikes. So we are the least committed to biological inspiration. We commit to a few key high-level principles, but not necessary to spiking neural networks. So basically, we bring some architectural concepts that are visible within the brain that we think are contributing to the efficiency from a practical, pragmatical point of view. We're not encoding, let's say, biological principles for the sake of just being biologically accurate. We're trying to take a more pragmatic approach. So basically, we sit at the level where all this brain dynamics is configured in software when we have some support for hardware at larger scale. So key things that we're committing to, we are committing to large-scale connectivity. We're committing to highly parallel systems. We are committed to distributed processing. We are committed to event-based computation. Event-based here is not necessarily spike-based computation. It's just this on-demand computation that you often see in biological systems. And the fact that you can program different units to have different characteristics and different programs. So this makes these systems very programmable in a way that they can sit into an overlapping area where you can implement neuromorphic principles, these brain-inspired principles. You can also implement regular deep neural networks, and you can also even implement what is known as symbolic, which was very famous in the 70s, that are basically rule-based systems that go very embedded into this type of architecture. So that's kind of the how it fits. So the connectivity at larger scale, I mentioned some of the key things we commit to. So essentially this type of architectures are interconnected at large scale in a toroidal network. So in a toroidal network, to make sure you always close the loop and you ensure the shortest communication path, you ensure that you can scale the systems, that you can interconnect the different units at really, really large scales while maintaining these key principles that I described at the beginning. So every point within this store is essentially a microchip, and then a microchip that is composed by a highly parallel mesh of processing elements. So every chip has essentially like a 2D mesh with 152 low power cores. And you can think of each of these cores as an edge device. So essentially, every of these cores is essentially locally constrained. You have this local constraints within the individual units, and you can think of this like this is a big microcontroller that have 152 low power cores. So somebody is asking whether the streaming got interrupted. Do you hear me, Petrut? Is everything good?
Yeah, all good, Hector. You can continue. So yeah, it works fine.
Okay, sounds good. Thanks. Yes, so then we have this highly parallel low power units, basically they are all interconnected, and that are interconnected with some strategic routers to essentially basically scale up these hierarchies. So what you can do is basically you can run individual cores with a very fine granularity, and you can run programs inside that core. You can think of this like you have 152 low power programs that are running that are not necessarily SPI based, and then you can run them in a very on-demand basis. For example, in this specific demo, actually we use a DBS camera, but it's only to kind of emulate the activity. You can do this with any type of activity, and what it's being shown is basically that when you go to a different quadrant, you kind of enable a new core while sending the other three to this extremely low power mode. You can do fine granular execution that is very difficult to do in regular GPUs, which are rather architected to be cascaded into multiprocessor streams. So it's kind of going for a different type of trade-off and a different type of paradigm, essentially. So then you take those chips, you interconnect them with neighbors within these hierarchies, you stack them into boards that basically elevate this hierarchy at larger scale, and you interconnect this into those toroidal networks at larger scale. You fold them strategically to make sure there's always the shortest communication path, and then you fold this into commercial data centers, commercial servers, essentially. So Petrut mentioned about the system in Manchester. So actually, this is a project that has quite a strong maturity and has quite a strong presence worldwide. So it was started by Professor Steve Ferber, who's the inventor of the ARM CPU, which is powering today more than 300 billion devices. And essentially, the Spinnaker architecture was crafted under his own ideas that were also originally generated into early work he did on asynchronous computing. So then essentially this is the supercomputer that lays in Manchester, and this is the second generation of the system that expanded this acceleration to cover more type of AI models. And it's a supercomputer that sits in Germany that has a massive number of low power processing elements. So the system is actually considered the world's largest brain-like supercomputer. It has been featured in Nature publications as having these extreme scalabilities and extreme levels. Key things, I mean, we work regular Python level frameworks so that you can deploy workloads using the regular deep learning frameworks. There are different intermediate representations so that you partition workloads that are sent into the machine so that you program. You don't have the struggle of essentially generating 5 million programs. You just work with a centralized interface in Python and you generate code for that supercomputer. This system essentially has several applications. We are commercializing it in different HPC centers, different supercomputer institutions, some selective enterprises that work with us that are very interested into this hardware-enabled algorithms that are trading off dense computation by these extremely sparse, irregular workloads. But I want to just focus on one of them, which is basically the one that relates directly into this overlap with the mainstream AI models that like everyone is familiar with. So essentially, when you look at the ecosystem of AI today, how it is architected by NVIDIA, essentially you have these training stages, you have fine-tuning stages, and you have this inference deployments. If you zoom in into the inference deployments, essentially you have specialized models that basically are prepared and pre-trained to be run at inference clusters. And then these models are actually being segmented at the moment. You have the models were traditionally very, very dense. So that dense meaning they were very computationally heavy. You have very, very dense matrix multiplication-based models. And there is a new generation of models that is a segment that is trying to search for training efficiencies, and it's going for adopting sparsity, like strong sparsity levels within these models. I mean, we categorize these models as slightly sparse. They are not extremely sparse as they can be. And essentially here is where you have all these regular companies that have been optimized for dense computation. You have NVIDIA, you have Samba Nova, you have Cerebras, you have Grok, you have all these GPU derivatives that are basically improving the execution of NVIDIA of computationally dense workloads. But then you have a segment of models that are basically kind of not reachable with the existing dense characteristics of these systems. So when you look at this dense, slightly sparse, and extremely sparse, so sparsity, you can find it in different levels, and I'm sure Jason in the last presentation will walk you through the exact levels of sparsity that you can have in different models at different stages. But from a very high level, you can have sparsity, for example, in attention, and you can also have sparsity within the MLP. So essentially, we're more interested in the MLPs because this is about 80% of the computational cost of these models. So any optimization that's done here has massive gains within the execution of this model. So essentially, when you have a regular dense model here, you have several paths that you have to compute in parallel, and then you start to segment those paths into what's known as mixture of experts, which is basically you segment the dense network and you create smaller subsets of the network and you activate those subnets in a very on-demand basis. So there is a router that is sitting on top and it's identified which expert to compute. And then the extremely sparse is basically going up to 1 million of possibilities, or even more, and then having only a small footprint that is computationally active. Mixture of experts is in generally a widely adopted architecture by now. There is like many models, like all state-of-the-art models are really crafted this way. And the reason also is because model builders like OpenAI, Google DeepMind, they are really searching for better training efficiency. So when you have an architecture composed like these layers with a mixture of expert type of architecture, you basically can characterize these workloads as the higher the number of experts you have, the better performances the models have. So actually, there have been a few MOE scaling laws that have shown that the higher the number of experts, the better performances your model get. So especially at these larger parameter counts, which is basically where it's more interesting for the state-of-the-art AI models today. So, but the interesting thing is when you scale this to very, very large number of experts, in a GPU, you no longer get like basically these computational efficiencies because there is a lot of routing overhead. So you can think of this like you have a heavy computational engine that you are misusing. So you are only using smaller computational footprints. So essentially you're misusing the large, vast amount of resources that you have in a GPU. So there are models that are touching into this extremely sparse direction. So Owen He, for example, from Google DeepMind, which he invented an algorithm that's called mixture of 1 million of experts that's extremely performant, but essentially it's very limited in terms of execution with the existing state-of-the-art hardware. The same with Meta. Meta has similar approaches that touches into a very large number of experts. That's memory plus blocks, for example, that are examples of those models that are touching the frontier of architectures to achieve very good training efficiency. You can actually see it here. I mean, the trend on sparsity models is very evident in this curve. For example, Llama 3 was fundamentally how models used to be very, very dense. You have then Llama 4 that started to be sparser. The 2 dimensions here, this is sparse activation, and here is fine granularity. So the actual paths that get active at very, very small. The higher here, the granularity levels is basically smaller, and also the higher, the more you go to the right is the more sparse activation you have. So then you have Llama 3 was fundamentally very dense. This is where basically all models were crafted like really traditionally. Then you have Llama 4 started to go for sparse activation. You have models like OpenAI that is going in this 120 billion parameter model that are very sparse. You have DeepSeek, you have Quinn, you have Kimi. There are other models that are going in this direction. What you see is that there is a very clear trend going to the upper corner of this graph. So there is a visible trend. That's what we call it, this inevitable trend of basically going into this extremely sparse activation region. And this is not even motivated by an energy efficiency metric. So essentially the main motivation is training efficiency. So basically, if you are a model builder like OpenAI, like Google DeepMind, you want to be designing models in this corner, not because they are more energy efficient. They could be energy efficient with this extremely sparse hardware, but essentially it's just because the model achieve better levels of expressivity. So actually the model is trained to be better. It's trained to have higher performance levels. But the problem is that hardware, essentially, where hardware today has the highest efficiency is not in this region. So basically GPU efficiencies and all these new GPU derivatives, they rather have the efficiency at the bottom side of the curve, which is where models started. So essentially GPUs are very good in this dense region. When it comes to this extremely sparse direction, they are very inefficient. So you have a very bad utilization of computational resources. So there is fundamentally a limit into basic that is constraining model builders to actually cross to this specific region. So that's why OpenAI is looking at alternatives to design hardware themselves, so that they try to crack into basically going to architectures that are hardware enabled, and that you can basically position models that are more performant than the state of the art. When you look at the architectures from a very high level, essentially NVIDIA has been optimized for this dense computation, dense computation. So they are very good in this region, and the new GPU derivatives, Grok, Cerebra, Samba, Nova, they are better than in this dense execution. When it comes to this extremely sparse activation, essentially, like all of them have a similar constraint, and is that the hardware has been designed rather for very large computation of dense, like dense primitives, essentially. So we position hardware that is complementary. So we basically this in hardware design, in chip design, you have a saying that is there's not a thing like a free lunch. Like there is always a trade-off. So essentially, we design hardware that's very good for these sparsity levels. So that means that if we have to execute like a very heavily dense model, we have a lot of scheduling overhead. But when it comes to this extremely sparse activation, like essentially you can impose hardware that only engage strategically the computational resources that are needed. And then that is what allows us to position infrastructure for those extremely sparse models, which is where the main industry in the mainstream AI space is essentially going. So that's my last slide. I don't know how long I did, Petrut, but I'm happy to take questions if I don't know.
Thank you so much, Hector. Yes, you are 2 minutes early. It's you're fantastic, very German. We do have a question. Let me see if I can pull it up on screen. I have my own questions, but we have a question of how can we leverage the benefits of Spinnaker in model training?
Yeah. Was this your question, or was this the other?
This is not my question. No, this is not my question.
So basically, there is a few work that we have done, but this is more on the research domain. So there has been a few work, implementation work that was done, for example, of the event prop, like this algorithm that was developed by the Heidelberg team. So we have a multi-core implementation of the event prop algorithm. There is also eProp. There is also other biologically inspired algorithms. So from a company perspective, we're not aiming to basically impose algorithms that are competing with backpropagation algorithms in NVIDIA hardware, because I think this is a quite tough task to do. But it's an interesting research question, and that is also being pursued by groups that are also very strong in the bio-inspired algorithm space. For example, Anand Subramani in the UK is also doing interesting work for training. So not an advertisement for him, but this is like basically alternatives for this type of approaches for this hardware that leverages training. But we're not doing it from a company perspective.
Is there any place where the research community could access your hardware to actually start looking at these problems?
So in the US, there is there will be an open access to the system, but in the US through the Thor project, maybe you guys can check it out. So the Thor infrastructure that includes basically few strategic PIs. There includes UCSD, UTSA, Harvard, and U Tennessee. It's basically centralizing access for some of the.
Right, and that might be interesting for some of the researchers looking to do training. I think there's also a question here, if I could highlight it, probably regarding other alternatives to neuromorphics. How does Spinnaker compare to advances in optical neuromorphics or frontier implementations?
Yeah, I think I briefly mentioned at the beginning. Let me pull this slide again. So basically, you have this you have this wide spectrum, right? So, for example, there are a few devices. I have seen memristor-based devices on this space, and indeed, I also came across not too long ago optical-based neurons. So this would sit within the device level. So basically, you have a spectrum. The more you go down, the more efficient you are at running spiking neurons, but then you have a few constraints in flexibility. So that's kind of a trade-off that you have within these different brain-inspired or neuromorphic.
I think there's also, I mean, for people who are interested, there's quite a bit of interest in spintronics and other material-based neuromorphic approaches throughout Europe, and I'm sure more widely, that could be of interest. I think my question is something about the timing. How does the timing feel? Why is it now the time for neuromorphics? What does 2026, 2025? What are these years? Why are they special?
I think what is interesting is this overlap with the mainstream AI community, that there is like a very strong interest in dynamic sparse systems. I think this did not exist before, right? So before, like, people were really like very occupied into just scaling models, like purely dense scaling, essentially. And now people started to see that there was a limit to how much you could do with pure dense computation. And then people started to search for clever ways to not massively scale the number of parameters, but like, how do you strategically engage computational pathways, which, if you think about it, is actually a research question that has been explored within the brain-inspired domain, and it's kind of overlapping. That's also why teams like Jason, and I'm also very excited about his presentation, are also looking at alternatives to actually bring this overlap between the two systems. So Jason is looking at it from an algorithmic standpoint. We're looking at it from a hardware standpoint. Essentially, how can you deploy these type of strategic hardware backbone to enable and cross the line of those hardware-enabled models so that you can shape the trend towards sparse models.
Okay, so because we're kind of starting to run out of time, there is one question that I feel segues very nicely, and just double checking with you if this is correct. There is a question here that I'm failing to highlight. So is there research for adapting already trained LLMs to run on hardware optimized for extreme sparsity, or does it require retraining a model from scratch? And you're saying that at the moment, you kind of need to retrain.
It's a great question. And basically, let me show you this. So basically, you have the...
And could we get a bit of support to see what Hector is sharing, because we can't see his screen at the moment?
Do you see my screen?
No, it's just us at the moment. Yes, now you can see.
So basically, the question that your question is touching a little bit, like, for example, essentially, if you craft models from scratch, you can craft models that sit on this corner directly, right? But indeed, as you pointed out, I mean, there is a cost of retraining models, which basically there is a cost to craft models in that upper corner. But we have, at SpinCloud, we have developed proprietary distillation pipelines that are basically not as expensive as vanilla distillation, and also not as expensive as retraining models, so that you can convert and sparsify layers, like these dense layers, into these peer-like layers. So essentially, we have a distillation pipeline that essentially helps you to take dense layers into this upper right corner. So that's kind of the like a key. It's a key component to kind of accelerate the adoption of these extremely sparse models until the full adoption of sparse models sits within that upper right.
Hector, thank you very much. There are a few extra questions. If you have a bit of time, do you want to try to answer them?
Yeah, I'll answer it in the chat. Yeah.
Thanks a lot. And we will go now to Matthew for him to give us his presentation. Hi, Matthew.
Yes, hi everyone. Like, very happy to be here. Very honored to present some of the work of my lab and my work. So my talk is called like exploiting biological priors for event-based motion estimation. And when I got like invitation, I asked Peter, so what the event will be about? What like the audience, what are the topics covered? And he says that one of the questions that we need to answer is what is the benefit of neuromorphic technology in edge tiny ML applications? And like I actually have a training in biology, and in my opinion, if we a bit like a zoom out from the particularities, the main benefit of like a neuromorphic bio-inspired technology lies in better priors, right? That lead to more efficient performance due to the constriction of solution search space. And particularities can be different. It can be what we care about in a stimulus, right? Like, for instance, in terms of vision contrast, how we transmit signals, like whether it spikes or not, how our neurons connected to each other. But the main thing is like it's just like a very good priors, right? And why biological priors are very good priors? Well, if you study a little bit biological systems, you will find that they actually cheat, right? The performance is often, and like I would say almost always, based on some very strong assumptions which are not necessarily true. So as one very good example, let's please look on these two images, right? And for most of the people, when you see this image, you would see some kind of the heel on the top image and some kind of the crater on the bottom image, right? Well, in fact, it's one image. It's actually bottom image. So now if we will flip top image, you should see that it's the same as bottom image. Maybe if you don't see it immediately, try to blink several times. So the reason why you initially saw it as a heel was that because we all operate under the assumption that light comes from above. But telescopical image, it gives you like an inverted image. So therefore, light comes from below and it should be a crater. But you assume that it's a heel because you expect light to come from above. And actually, this is like very well-known phenomenon. Basically, all the early like heated debates between early astronomers on whether moon has craters or mountains, they were all like caused by this phenomenon, right? And it's just one example. We can go even like further. For instance, thoughts, they're very good at tracking stimuli that are horizontally oriented, but very bad at tracking stimuli that are vertically oriented. And the reason for this is that they usually hunt worms who has a horizontal orientation. So basically, biology overfits. Biology is based on some very strong assumptions, but it's a good thing because these assumptions, they often reflect properties of the real world. And it's actually, you can see it even if you study neurons on a very low level. So for instance, if you talk about cone photoreceptors that we use for the daylight vision, right? Their gain to encode contrast is very asymmetric. It has like a higher amplitude for the negative contrast versus positive contrast. And the reason for that is that in the natural scenes, usually distribution of light intensities is like skewed. So basically bright contrast, they usually have high amplitude, but they are less frequent. And negative contrast, they have small amplitude, but they are more frequent. So as a result, cone photoreceptors use this like a nonlinear gain to provide some symmetric output. So basically, it's useful to study biological systems to create neuromorphic technology because then you can get a good prior, good initialization for your system. And of course, you shouldn't follow biology blindly, right? Because evolution is random, undirected process. So there is like lots of junk DNA, a lot of like a legacy code, which, it's there. So the rest of the stuff needs to work in light of it. But it's good for extracting some general principle and then building upon it as an engineer. And in MAVLab, people have like a very particular interest in neuromorphic technologies because they present possibility to develop very efficient systems. Because as the name of our lab, it's like a micro air vehicle lab suggests, we are very interested in micro, very small drones, and we want them perform to the highest extent. So for instance, one very impressive, in my opinion, example is the Delphi Nimble that was developed in 2018 by some of my colleagues. And this small flapper drone, it's like has wingspan of 33 centimeters. It has very small weight. It uses for its operation some microcontroller, right, which consumes only 0.2 watts of power. But both like a processor capabilities and as well as memory is quite limited. So to perform efficiently, it really needs to leverage some very efficient neuromorphic technologies. And that's kind of was the main motivation why our lab started investigating neuromorphic technologies. And so now, if you talk about neuromorphic technologies, what are, like, let's say, the main tools that are used in our lab, but also in other labs focused on robotics? Well, two pieces of technology, like, it would be essential, right? So first of all is event-based cameras, right, which were developed in Zurich in a group of Toby Delbruck. And their output resembles output of the retinal output cells, right? So basically, if you will look this video compares what is filmed by the frame-based camera on the left and what is filmed by event-based camera on the right. And as you can see, so first of all, is that like event-based camera, it transmits only contrast, changes in light intensity, right? Which is like aligned with what biology does. And also it's very fast and very asynchronous processing, right? So we only transmit from the pixels where there is change in contrast, not from all the pixels. Therefore, if we will spin propeller very fast, but like a slow down replay, you will see that like a frame-based cameras, at some point it creates motion blur, but event-based camera is not susceptible to the motion blur. So these event-based cameras, they like perceive only brightness change. They provide as an output sparse event, and they're very fast and energy efficient. So compared to traditional frame-based cameras, in terms of latency, they give you like up to basically frame rate of like up to 1 kilohertz. You can actually go even further, but like, and in terms of energy efficiency, the gains are like a couple of orders of magnitude. And this event-based camera, they work the best when they paired with a specific processing devices, right? Usually called spiking neural networks, which are also heavily inspired, of course, by the communication in the brain. And just to quickly illustrate how spiking neural networks work, basically they have some receptive field which collects signal from other cells. And as soon as the sum of this signal exceeds certain threshold, as their output, they fire some sparse spikes. And it's very efficient because, like, so spikes, they have, in this case, they have fixed amplitude. It's either 0 or 1. And as a result, all of your connectivity between neurons, right, you don't have multiplication operation. You have only summation operation. And as a result, the entire system behaves much more efficient, right? Plus, like, because you threshold and signals, you have like a very sparse output, which is, yeah, also very energy efficient. And these spiking neural networks, they usually can be run on neuromorphic processors, right? And now there's like a huge number of different neuromorphic processors on the market, starting from some processors from Inatera, like T1, Pulsar, but also there is like a Luigi from Intel. There is like a aforementioned Spinnaker. There is like a Hican processors from IBM. And there is like the research in this field is ongoing because, like, if you will go to some neuromorphic workshop, like to Capocacha, there definitely every year will be a couple of people with, their own newly developed neuromorphic processors. And despite this technology being novel and cutting edge, it's already quite mature. So as a result of years of research in our lab, we were able to achieve, well, not we, my colleagues were able to achieve a certain milestone. Basically, so the drone, right, it equipped with event-based camera and neuromorphic processor, and it was like they were able to use images from event-based camera for processed by the spiking neural network implemented on a Luigi chip for drone navigation, right, like a successful landing, successful flight. So here in the bottom you see the pipeline. You just have events. They go to the vision network that provides like a control commands. And here is just like what actually going on. So for energy considerations, they measure only optical flow from 4 corners, right? This is like events from event-based camera. Brightness changes, green increasing light intensity, red decreasing light intensity. And then like, there is like a spike and net, which provides control commands. And it's very impressive because if you will compare it with, like, we can run this network on some neuromorphic chip, like Intel Luigi chip, right? And then you see basically how much power it takes, like idle power and also running power together with inferences per second. And then we can compare it with the performance on NVIDIA Jetson Nano GPU. And you can see that although like idle power is very similar, but in terms of like a running power, in terms of inference per seconds, implementation in neuromorphic chip give you like a 1,000 or even like almost 10,000 times improvements in energy. So this is all very great, right? But this is all was based on some generic neuromorphic considerations. Like let's say, let's have spike in sparse signals. Let's process only change in light intensity instead of the entire frame. But can we get more if we will be using some more even more bio-inspired approaches, right? Where we will be looking on particular architecture of biological neurons and we'll try to implement in our engineering context. And this research topic was particularly interesting for me when I joined the lab, because I have like a background in biology. I actually was doing electrophysiology, and I was studying properties of some individual ion channels and how they affect signal processing in neurons. So it's like all very detailed, granular approach where sometimes you don't see forest behind the trees. And I was interested to see whether detailed neuronal models are useful in engineering context, right? And as a starting point, like let me tell you about some piece of technology developed in Groningen in a group of Elizabeth Kika. It's called like a time difference encoder. And this is inspired by a very old, like from the 60s, model of elementary motion detection in insects. So if you will take a look on this fly, if we will zoom out on its eyes, right? Its eyes are organized into, like, as you know, they don't have like a one big eye like we, they have like a multiple individual ommatidias, right? It's called, you can think about it as pixels. And motion detection there works like so. So assuming you have some with a, yeah, so let's assume we have a ommatidia, let's assume that we have our time difference encoder, and let's assume we have a moving edge, right? When edge passes through one input called facilitator, it creates like a decaying gain, right? Such that when it passes through another input called trigger, we convert this gain into current that like it charges, of course, membrane of this time difference encoder and provides output spikes, right? And this thin time difference encoder, it can be, of course, implemented in a software, but in Elizabeth Kika group, they also implemented in a hardware. And as you can see, the working principle is very simple. You just look on a correlation between two spatial points, and you can extract direction of motion and even speed of motion, because if basically if there is like a fast motion, then the gain will decay less, current will be bigger, and hence you'll have more spikes. And in Elizabeth Kika group, they were able to achieve quite impressive results with these time difference encoders. So for instance, using this time difference encoder incorporated in a slightly bigger network, so you have like an event-based camera that provides events as an input. Then you have like a two stages, like spatiotemporal correlation filter and onset, which are important for signal to noise ratio. And then you just have two time difference encoders, one tuned from left to right, another tuned from right to left, which drive robot motors. Basically, you can achieve with only 4,000 neurons, and the robot was able to do some like a corridor centering, as you can see here, right? So it uses event-based camera that feeds to, just into the pipelines that I described. And with only 4,000 neurons, drone is able to move in a corridor, but not only that, it's also capable of collision avoidance. So here you see view from the top, drone is just orange dot. And using this like a very simple optical flow processing pipeline, it is able to navigate through obstacles quite safely and without collisions, right? However, this time difference encoder, despite its obvious very good performance, has a one big issue that is like that hinders its performance. So basically, this issue is that in a highly textured environment, individual time difference encoders, they lose their direction selectivity. So for instance, here you see, again, moving edge, it goes from right to left. And then when it passes, so basically this detector is tuned from left to right. But what will happen is when edge is moving in opposite direction? Well, initially, if it's just only one edge, it all works fine, because when you have trigger, you don't have anything in gain because facilitator was not activated. So there is no current, so there is no spikes. The problem is when edge is finally passing through facilitator, it creates some time decaying gain, such that if second edge is moving closely after this first edge, right? Now there will be some time decaying gain to convert to current, to produce spikes. And as a result, we will be reporting motion from left to right, although there is only motion from right to left. And if you make more like a large-scale experiment, so assume the drone, it flies over the textured environment, right? And then, so this is the direction of the optical flow, and we were using these time difference encoders to estimate this optical flow, and we will compare outputs of the time difference encoders tuned to 4 cardinal directions. You will see that actually, like in textured environment, motion direction estimation with TDE is only 11% better than guessing, right? So you clearly see that although we were moving only in one direction, the spikes were coming from all types of time difference encoders. And in principle, you can solve this problem by establishing some winner-take-all mechanism, such that outputs of 2 oppositely tuned detectors will inhibit each other. But it's not efficient because the spikes from individual detectors will still be occurring, right? You can subtract it later on, but presently spikes will still be there. So instead, we decided to develop more advanced versions of this time difference encoder, right? Which was even more heavily inspired by biology, because as I was mentioned, this initial time difference encoder was inspired by classical model of motion detector, which is from 60s, and we used something that incorporates recent discoveries from like 2019. And these discoveries show that actually elementary motion detectors in insects, they collect inputs from 3 spatial locations like facilitator, trigger, and inhibitor. And because you have this like inhibitor, right, which resets gain to 0, even when there is like a motion in opposite, even there is like lots of texture move in opposite direction, because of this constant reset of facilitator, you retain your direction selectivity. Such that if we will repeat the experiment from the previous slide, right, in ideal condition, yes, basically it will be only spikes in a preferred direction. Of course, if you will, in a very real world experiments when there is noise, it doesn't work that well, but still it's like, even in the real world, since TDE3 has almost 2 times higher direction selectivity than TDE2, right? And then you can use it for real world optical flow estimation. So I see that I'm close to run out of time, so I will speed it up. Basically here, both types of detectors perform just as well, right? But TDE3 spikes less. And then, of course, you don't need to use it only in some like a laboratory stimulus like this. You can also use it for the ego motion estimation in driving sequences, like we did here. So on top, you have like an output from the event-based camera. On the bottom, you have output of the ego motion estimation with a network of time difference encoders, right? So like turn to the left is here, turn to the right is there, and we compare output of both TDE3 and TDE2 with ground truth, and you can see that both of them follow ground truth quite veridically. And even more than that, right, if we now benchmark it against other methods of estimation ego motion from this data set, right, we see that the TDE2 and TDE3 compare on par with the SOTA. And I would like especially put your attention to this fact that here you see our performance is very close to this performance from reference 59. And here they used neural network with 150K parameters, right? So looks like this time difference encoder are really very powerful prior for motion estimation. And current research in our group is focused on using TDE3 as a prior for onboard learning of depth, right? So the idea is the following: you have a drone, you have like a TDE output from event-based camera as like a visual input, right? So as TDE is estimated normal flow, so that's why you see sometimes like several colors here. And then these TDEs, they feed into the neural network, right? Which is like also quite small. And the idea is that we will use another like a bio-inspired learning methods, for which I don't have time to discuss for the interest of time, to teach the network to learn estimate depth from the TDE outputs while using data from time of flight sensor or from LiDAR as a supervisory signal, right? And why we need to do it? Because you can gain some benefits from this sensory fusion, right? So here we it's like our preliminary results. We did exactly this. On top, you have ground truth. On the bottom, you have prediction, right? So ground truth comes from the LiDAR, prediction from event-based camera. And as you can see, basically one of the benefits why you can use this sensory fusion is that you can estimate depths in the points where LiDAR does not give you depth for one reason or another, right? And of course, what you get with a network is more blurred than ground truth. That's because our input is very sparse, but during constructing depths, we use like a bilinear interpolation, so you see some, it's more like a smooth and blurred, but yet in terms of numbers, it performs quite well because mean absolute error of our depth estimation is about 36 centimeters, right? Given mean depth in a scene of 2.5 meters and standard deviation of 1.6 meters. And although our performance is 3 times worse than SOTA, but it requires only 60K parameters versus like 1 to 10 millions that you see in a state of the art, right? And another benefit, so I showed one benefit is that you can estimate depths where your LiDAR or time-of-flight sensor cannot. Because of another benefit is that event-based camera is very fast, but your LiDAR or time-of-flight sensor are much slower, right? So now using this training pipeline, you can also estimate depths in the frames which is not available from the ground truth, which will be showed here, right? So, I mean, and as you can see, it's like it quite works basically, right? So with this, I guess I need to wrap up because I'm sure I went over time. I hope I was able to convince you that bio-inspired priors are useful for efficiency. And I would like to thank our founders, which are like, Air Force Lab, Sony Research Award Program, and European Space Agency.
Matthew, thank you very much. I'm sure there's going to be questions rolling in soon. I was very curious, what kind of like requirements would you need for a neuromorphic chip to actually be able to run all of this on board? What are you looking for a system, a chip to do?
I would say Loihi 2, right, can be quite appropriate, right? Because it allows, I mean, because, so main thing, if you want to combine it together with like a bio-inspired, what chip should allow you, it should be flexible in terms of like a neural connectivity and neural model, right? So some chips, they give you only leak integrated fire neuron or only integrated fire, but here, as you can see, we need a bit more complicated interactions. So that should be the case, that we can tune neural models how we want. Also, like neural connectivity also should be like a flexible, because we want to have models where we have two types of connections, like feedback and feed forward, and they need to be separate. So basically, chips with tunable neuronal models and tunable learning rates will be the best.
Do you see a path for? I'm still waiting for questions. There are a few comments in the chat that I think would be interesting for you to have a look and maybe respond, because they're more comments than questions. I'm curious in terms of how you see the future of training models like this. Is it you presented quite a few methods that, in my experience when I was doing my PhD, they take PhD time to be able to optimize and tune and make sure that they function correctly. What does the future look like? Is it AI agents or automatic auto ML systems that can tune these kinds of, how should I call them, primitives?
Yeah, I would say, the future is blindingly bright, but it's very far, right? So like in principle, time difference encoders, you don't really need, I mean, you can tune them manually, like, so time difference encoders, the only thing that you need to tune is that you just want to have like to be able to encode a certain range of velocities, right? For this, like a conventional methods, like a backpropagation work quite fine, right? But then if you want to also have very efficient on-board learning performance, where you want to use this like a burst-dependent synaptic plasticity, which I just like barely touched. There, it's like I was able to get some good performance out of it, but it requires like a lot of engineering. So I think, the future requires like a lot of work, but luckily there is like more and more groups that adopt working on these birds. So for instance, in Richard Noah group in like a in Canada. They already implemented it on even in neuromorphic hardware. So I would say it's more research than technology, but potentially it can be technology.
Okay, thank you. And we also have one question in the chat. Do you see life science application within Mav Labs? Or do you
Yes. I think like it actually has enormous potential for the life science application. And the reason is that if you like use drones or generally robots, right, it's a really good model organism. Because if you study animals, of course, yeah, it's like a real animal, but you don't have really much of a control of the system, right? And you cannot really access all of the neurons, or you cannot access all of the neurons in an animal with high resolution. However, if you use a robot as a model animal, as a model organism, right, then you can test some basic biological principles in a real world context while having like a lots of control over the system. So I think it's actually, for instance, we collaborate together with people from Wageningen University, and they use this like a Delphi and Flapper robots as a model of insects, right? Because it captures general properties of the system while giving you like a full control. So it's like a nice to test biological. It's the best medium to test general biological theories.
Matthew, thank you very much. I think that's what we kind of had time for at the moment. And so, yeah, thank you again. And next up, we have Jonathan Tapson. And Jonathan, are you? Hi, good morning.
Hey, good morning. How's everybody? Can you hear me okay?
Everything's working well, yes.
Okay, let me share my screen. Okay, you should see my my title slide, and I hope that it's displaying okay.
Yes, it looks perfect.
Excellent. So I'm the Chief Development Officer for BrainChip, and BrainChip was the first company to market a commercial neuromorphic chip, and still one of the only companies doing this, and therefore I thought it might be interesting to just talk about some lessons from commercial neuromorphic chip design, because I think this is a community that is mixed between research and commercial backgrounds. So just a quick outline. I'm going to give some perspective, and then I'm going to talk about a number of features that affect chip designs and how. I'm not going to go into too much detail about how BrainChip has specifically addressed them, but I will give some indications towards the end. So if one's going to offer perspective, I wouldn't normally put up a slide describing my experience, but perspective, it's implicit that you have a point of view, and so I want to give a little of my background. I was for many years an academic and research leader at a number of universities, and specifically co-founded with Andre van Schaik the Bioelectronics and Neuroscience Group at Western Sydney, and that is now the International Center for Neuromorphic Systems. And then my last academic job was as director of the Marx Institute for Brain Behavior and Development, which is the parent institute of the ICNS. And then for the last decade, more or less, I've been working in industry as typically a chief scientific officer, chief technology officer, or chief development officer in commercial chip companies. One of which was Grey Matter Labs, which was acquired by Snap, as in Snapchat, a couple of years ago. Okay, so first of all, just neuromorphic is a loaded term. I think Hector earlier referred to this. This is Google search trends for neuromorphic, and you can see that neuromorphic's having a moment. But I can tell you that 5 years ago, particularly, it was brave to put neuromorphic as a marketing term around a chip. And when the founders of BrainChip decided to very explicitly call it a neuromorphic chip company, that wasn't an obviously a good thing. It is now, but there have been times, and there may well be times in the future when this was quite an ambiguous or ambivalent term. Some of you will have seen this recent article from our colleague Giacomo Indiveri. Giacomo was being provocative, and basically saying that because of the popularity of the term, It's becoming overused, and he made the point that neuromorphic was originally coined to refer to analog electronic systems designed to directly emulate the fundamental operations and strategies of the nervous system. So he was making a provocative point that we've come a long way from the original vision, and we should be getting back to that. What is interesting to me is that if you look at companies, there have been a lot of successful companies that have integrated neuromorphic technology already. Okay, going back as far as the earliest optical mice from Logitech had a neuromorphic, actually very similar to the system that Marcus has just outlined. They had a neuromorphic chip doing the optical tracking. Samsung phones have over the years integrated neuromorphic audio chips. They just aren't called that. And I'm always reminded of a statement from an Australian comedian called Tim Minchin. He was ranting about alternative medicine, and he said, we have a term for alternative medicine that works. We call it medicine. And similarly in neuromorphic engineering, I think by the time neuromorphic engineering gets adopted into working industrial systems, it loses that term. And that's not necessarily a bad thing. It's just something that happens. So I want to talk momentarily about the gap between academic or research neuromorphic systems and commercial electronics. And without going into these in detail, neuromorphic systems tend to be analog or mixed signal. They're asynchronous, they're stochastic. Their models are black boxes. They're event-based and sparse, and they're intrinsically parallel. Whereas commercial electronics, such as the computer I'm actually using to talk to you, they're digital, they're synchronous, they're deterministic. Machine learning notwithstanding, almost everything that happens electronically is interpretable or explainable. They're periodically sampled, and they have the von Neumann bottleneck. And this gap is interesting from a research point of view, but it's a bug from the point of view of selling chips, because every single one of these issues is a barrier to adoption. And I want, stepping out of neuromorphic for a second, I want to just address, for example, asynchronous and synchronous electronics, because this is a fundamental feature of electronics design, completely independent of neuromorphic systems. So asynchronous design typically saves about 40% of the power. That's the rule of thumb in an electronic circuit, and very often the circuits run faster. So there's almost no downside to designing asynchronous electronic circuits, but the adoption of asynchronous design is less than 1%. And when I say less than 1%, it's probably less than 0.0001%, but we just don't know where to put the decimal point there, because this is not something you can measure with any accuracy. There are companies that specialize and highlight the use of asynchronous design. Acronix is probably the best known one, but these are not, the names are not Intel or NVIDIA, and so I bring this up because very often the performance benefit of a specific design choice may be obvious, but it doesn't directly lead to or cause adoption, and you get headlines like this from 2 years ago in semiconductor engineering, which is kind of baffling. And I can't explain this to you. I can't explain why the adoption of asynchronous is less than 1%. I'm just saying that the obvious benefits don't lead to obvious adoption. And this is something that we need to be aware of. Okay, so I want to talk for a moment about a typical kind of design feature going from biology to electronics. So in biology, spikes are canonical, and it's a basic unit of information. We start abstracting that in neuromorphic electronics as a Dirac delta, and that is itself a significant abstraction. But we can't embody a Dirac delta in electronics, so we wind up with a pulse, and you think, okay, this is okay. But when we actually build a circuit of significant size and start passing spikes around, we find that we have to pass them as, for example, AER packets. So here's three three large-scale chips that I know about. So Loihi uses a 32-bit AER packet. Grey One used a 19-bit network on chip packet. True North, I'm not sure of the exact number, but it's more than 30 bits. When you see their address sizes, it's got to be somewhere north of 30 bits. So what does this mean? It means we're spending 30 bits of energy to pass this beautiful 1-bit spike, and so the energetics of the beneficial energetics of using spikes are pretty far gone by the time you're building these big systems. And an obvious response to that is that you might as well not send just a spike. You might as well send more data, a number, 4, 8, or 16 bits, because if you add a 4-bit value to a 19-bit packet, you haven't really changed the energetics of sending that information, but you've dramatically increased the amount of information that you send. So this is the kind of path from biology to engineering that tends to get followed when you're designing these chips. I want to talk for a moment about physical scaling of memory. And this graph, which is log scale, shows the density of SRAM over not quite 2 decades. And the two dots represent Samsung and SK Hynix memory density. And you see that, SRAM has not quite increased tenfold in density over 2 decades. Why SRAM? Because SRAM is the bread and butter memory technology for computing memory, which is the kind of what pretty much all neuromorphic chips are. Okay. But one of the problems with SRAM, it's not really scaling anymore. It hasn't really scaled since about somewhere around 12 nanometer to 7 nanometer. It just stopped effectively scaling for various technology reasons. So we have other kinds of memory. We have DRAM and flash. And interestingly, they are both more dense than SRAM, but they also seem to still be scaling. And again, the flash, you notice there's no number there after 2023. It's quite possible that all these technologies are scaling, but these other memory technologies have scaled much better than SRAM in a lot of ways. Okay, so and to the point now where flash is almost 100 times more dense than SRAM. And you might ask, what about MRAM, ferroelectric RAM, ReRAM, phase change memories, and so on? They have potential, but when you put them on this chart and you realize that memory, DRAM is now being produced in 3 nanometer technologies, they don't really show up very, very well. So there are lab results showing them being semi-competitive, but Samsung's most recent announced number for their MRAM is way down here on this thing. So it's easy to forget how intensely effectively the conventional memories have scaled and how far the new memories have got to go to actually show up. And why does this matter? Okay, here is now models on the same curve, on the same graph, logarithmic scale on the right-hand side, but each line still represents a decade of expansion. And you see that the scaling curve of models is dramatically faster than the scaling curve of memory. And we keep hearing about the end of the scaling era, but it's like the end of Moore's law. It's not actually happening. So we have to respond to this as commercial electronics people. So just to put this in perspective, here's a comparison of a gig of memory to a United States dime or 10-cent piece, which for those of you who are not Americans, this is about a 19 millimeter diameter coin. And you can see that a gig of SRAM is huge and a gig of flash is microscopic. And this matters. It matters a lot. Remembering that when you sell chips, when you manufacture chips, you're paying for area. And area really matters. Also, yield goes down dramatically as the area of a chip goes up because a single point flaw can take out a whole chip. So just for comparison here, here's a typical computing memory chip with 8 megs of memory in a kind of neuromorphic node, a good neuromorphic node, 12 nanometer TSMC. For computing memory, you're typically blowing up the size of the actual memory by about 2.5 times because you're putting compute in there and network on chip and so on. So you see that 10 megs or 8 megs of computing memory is about the same size as a gigabyte of DRAM. So that's a factor of 100 different. So these are things we have to contend with. And one of the conclusions I have is that computing memory based on SRAM certainly, and I believe based on anything that's available today, doesn't appear to have a path to handling these rapidly scaling Gen AI models. So we wind up saying that computing memory is going to be good for just niche applications where you have extreme low power, where area doesn't matter, or where you're using CNNs and RNNs with relatively small parameter counts. So let's talk for a moment about machine learning and AI. We had a paradigm change, okay? And from 2012 with ResNet to 2017, almost everything was CNNs. 2018, we start to see transformers, and nowadays, I would imagine the massive majority of compute goes into transformer or analogous networks. And this is important because CNNs use small weight kernels applied to many input variables. So you actually had a small number of weights involved in a lot of compute. So a typical CNN, you might do one memory fetch or need one weight for 50,000 max, multiply and accumulates. So a massive amount of compute going on for a very small amount of memory fetching. Whereas transformers particularly, it's one weight, one Mac. So if you have a 600 gigabyte weight space, you fetch those 600 gigabytes, use each weight once, and you throw it away in an inference typically. This is simplistic, but not inaccurate to first order. So suddenly you're doing one fetch per Mac. Why does this matter? It matters because a second factor affecting this is that until maybe 3 or 4 years ago, there were no commercial, there was no AI, there was no open AI, there was no ChatGPT. Effectively, the vast majority of compute used in machine learning was going to training, and training is intrinsically parallelizable. So this didn't really matter. You could fetch those weights once and keep them in memory and use them a lot of times. But now with more inference than training, and particularly on the edge where everything is batch equals one, everything happens once. You have to fetch all those weights every time you do an inference. So in computing, we use these roofline diagrams, and we say that any compute system is bound either by memory bandwidth or by compute performance. And the interesting thing is that all CNN workloads tended to be bound by compute performance because you had to do so few memory fetches. Whereas now, suddenly, for the last 4 years, we're in this different part of the paradigm where everything is bound by memory bandwidth. And just to give you, I think I have before I get there, just a reminder, why does this matter? It matters because memory fetches are very expensive in terms of energetics. It's one reason why compute and memory is the only reason why compute and memory has commercial application is that fetching memory is expensive. Fetching memory from on a chip uses twice as much energy per rule of thumb per byte than doing a multiply operation. Fetching from off-chip flash is 20 units, and fetching from off-chip DRAM is 100x the energy of doing that Mac. Again, these are first-order approximations, but they're surprisingly useful. So suddenly memory fetch is the only thing we care about. If you take a typical LLM workload on the edge, and I know Jason Ishragian is going to talk more about this. I hope I'm not contradicting anything he's going to say. But if you imagine a 1 to 8 billion Gen AI workload, you want to do about 20 tokens per second, a token being a word or a subpart of a word, a syllable, if you like. You have linear or quadratic compute requirement as the context length goes up. But the first token you need to fetch, the first few tokens, you need to fetch 160 gigabytes of memory every second, but you're only doing 160 GOPS, not TOPS. We don't need a teraop of compute to do this workload, but we need to fetch 160 gigabytes every second. Okay, so let's talk a little bit about data movement on compute and memory chips. So here's a kind of cartoon of a compute and memory chip. This is our 1 gigabyte, our kind of prototypical 1 gigabyte compute and memory system. It's a big chip. In the best process node today, this is a 19 millimeter by 19 millimeter chip. And that's a big chunk of silicon. It's going to cost well over $100 to fabricate. Okay, and the fact is, compute and memory says, keep the weights static, pass the data through because there's always far more weights than there's data. So this minimizes memory movement. That's the entire principle of computing memory. But nonetheless, if you move data from the top left to the bottom right of this chip, it may have stayed on chip, but it's moved a long way. It's moved more than 19 millimeters, moved maybe 25, 26 millimeters, just to assuming a straight line, and nothing travels in a straight line on a chip. So it's actually, you can do a first order model of this. You can say, if I have a computing memory chip and I have the equivalent on old school for Neumann compute, where I've got just some DRAM and a little piece of compute silicon, and here they are put to scale, you suddenly see that, okay, I may not be moving much data on this chip, but I'm moving it a long way. Whereas in this arrangement here, I'm moving a lot of data, I'm moving the weights rather than moving the data, but I'm not moving it very far. And you can actually model this. So what you come up with, your metric is gigabyte millimeters, meaning how much data did I move, how far, and a smaller number is better. And for a typical 1 gig model, you find that computing memory still wins. But remembering that computing memory scales up at 2.5x, just the size of just SRAM, for example, you actually find that there's a crossover point. And in this simplistic model, which I'm not going to go into because it's proprietary, it's not that simple, but you find that the break even for these kind of systems is probably somewhere between 1 gig and 2 gig. And it might, if you use different memory or different process nodes, that is going to move up and down. But the point is, this is right in the area where we're trying to operate. So moving on a little bit, let's talk about software stacks, because if you are going to offer a commercial chip, you have to have a software stack. And I note that approximately, nobody knows the exact number. I think Jensen Huang has said it's about 70% of NVIDIA's engineers are software engineers. So NVIDIA is a silicon company. They sell silicon. But 70% of their people actually are involved in making sure that their silicon has something to run. And that is actually a rule of thumb across hardware companies. Most hardware companies are actually software companies that sell silicon. And just this picture here is from Google. It's the Coral NPU software stack. And it's an indication of why. Why do I need so many software engineers? It's because as a commercial vendor of silicon, I have to have all of these features working for my customers. And if I haven't got this software stack, I'm not going to sell silicon. And it doesn't have to be obviously this one, but the point here is this is actually just a basic stack. It doesn't include it's assuming that your customers already have their models in the form of PyTorch or JAX or TensorFlow or whatever. Okay, so it's already quite a simplistic process. Let's talk for a second about network models. Look today at Hugging Face. There's 2.5 million models on Hugging Face. I did a rough API search that may have been a bit ham-fisted, but I found less than 250 which had spiking in the model name. And mostly when people put a spiking model on Hugging Face, they put spiking in the title. So this could be out by, it could be 1,000 times. If I got my orders of magnitude right, I think it could be 1,000 times too small of a number and still be less than 1% of the models on Hugging Face. So why is this important? It's important because it means that the engineer in the street, the machine learning practitioner in the street, is very likely not a spiking neural network person. So you have to, as a company like BrainChip, you have to facilitate them converting it. And this is a complicated process. There has to be an algorithm, and selection of that algorithm is in itself a specialist issue. You are asking the customer to expose their proprietary data set somehow for retraining. And that by itself is most companies will not expose their proprietary data to a third-party vendor. So you have to provide them with tools that they can use behind their firewall. And they have to have confidence in the security of those tools. So we have achieved this in BrainChip. We're proud of that, but it's hard work. And then again, if these models are large, if they're gigabytes in size, you're paying non-trivial amounts of money to do retraining, and then you have to test and validate. So all of these are issues that stand in the way of adoption. Okay, so I have a few conclusions. The first is to remember that neuromorphic as a marketing term has ambiguous value at this moment in time. I'm not sure if that's good grammar, but it's I'm sure you understand the point I'm trying to make there. As commercial chip companies, you have to make very careful choices about which features of neuromorphic engineering you're going to adopt and put into practice in your chips. And BrainChip has, I think, done an incredibly good job of sort of navigating this pretty narrow path between keeping the good and losing the difficult. And I think if one thing this talk may have persuaded you of, that there are a lot of difficulties to adoption. So BrainChip's circuits are synchronous and digital and deterministic because our customers demand that. They want to fabricate silicon using standard processes. They want to use standard design methodologies, and they want to be confident that the chip does what it says on the box. But nonetheless, we use event-based, we use graded spikes because why not? You might as well pass 16 bits or 8 bits. You get a lot more. Converting networks becomes a lot easier if you're not converting them down to binary spikes. If you're keeping your information as 8 or 16 bits, it's much easier. We have a very comprehensive software stack, and we have a design philosophy which says for small chips, use computed memory, for large chips, use monolithic memory, which is for the reasons that I outlined earlier on. And then one always has to acknowledge that adoption, and I gave the example of asynchronous logic, adoption is not necessarily sensible or logical or even based on performance. You can have incredibly good performance reasons for adopting new technologies, and they don't actually apparently seem to take hold. So we need to recognize also that neuromorphic approaches, I didn't go into this much, but a lot of approaches which work in the lab don't scale industrially. And there are the recent history of startup companies is kind of littered with some examples of companies that haven't made it. And I think some of the early decisions made in BrainChip were really good from that point of view, in terms of just having the company be successful. And also I want to say, though, if you're interested in this field, keep trying, because there are actually many more successful neuromorphic companies than are commonly recognized. And this comes back to the fact that by the time neuromorphic engineering gets adopted, very often it doesn't have that label anymore. So you have almost certainly used a device with a neuromorphic chip in it. You just didn't know. And a lot of the people, and in fact, even some of the designers designing those systems probably didn't know that they were intrinsically neuromorphic. Yeah, so that is where I'm going to stop today.
Thank you very much.
Chip in the pipeline that will be optimized for generative AI workloads.
That's fantastic. A quick comment on the conversation. Do you have any quick comments on the conversation that's been going on in chat? I'll just summarize it for you. There seems to be a thought in the chat that the reason why asynchronous design hasn't really picked up is because EDA companies don't have an incentive, or they simply haven't supported it enough. So it's a chicken and egg situation.
I think that's accurate. I know Raj Manohar at Cornell who is one of the main evangelists of async design, has, I think, an open source EDA toolchain that's actually very good. I would encourage anybody who's interested to look at his work. But that doesn't really answer the question. I mean, it's a reason, but if you're leaving 40% of the power used in electronics in the world on the table just because they aren't EDA tools, that doesn't really make sense. So I don't have an answer as to why async. And in fact, one of our community who may be online, Steve Ferber, the founder of ARM, has, I know, for many years been encouraging the use of asynchronous design, but he might well be better positioned to answer that question.
His retirement party had one hell of a conversation from all angles about asynchronous design and how good it is. But okay, thanks a lot, Jonathan. I think that's kind of the time that we had for now. And Pete, can you take over?
Yes, I'm going to introduce you. Those who you are now that have been watching the live stream. But yeah, it's Inotera is one of our strategic partners, and I know you've been dedicated to the space for a long time. And so why don't I give you the floor and again, folks, love the comments, love the chats. Let's keep it coming, and we will cut in toward the end of your talk and get some live Q&A going.
I'll even time myself. Thanks a lot, Pete. My colleague Federico was meant to give the talk, but here we are. I hope that I can do the talk justice. There have been some conversations in the chat about the commercial applications of neuromorphics, and Jonathan touched on them a bit earlier to some extent. So what I'm going to focus on is basically some of the applications that we have, then some of the use cases and deployments that we have with our chip from Inatera, with a quick introduction of what the company is. So it's a spin-off from TU Delft that got incorporated in 2018. We're roughly 110 employees at the moment, mostly in Europe, but we're headquartered in the Netherlands. And we've raised over 55 million in venture capital funds to build, I'm not 100% sure at this moment, 6 or 7 generations of silicon that we are aiming at all kinds of sensors. So sensors are everywhere. There's so many. There's 10 per phone, with speakers having a couple, wearables having 5, offices having hundreds to maybe thousands, and they come in so many varied different interfaces, data rates, etc. So we're trying to take a part of this and then to add intelligence to these sensors. In a power budget that is similar to what the sensor actually consumes. At present, AI deployments can be relatively inefficient because they generally rely on deploying machine learning models either in the cloud or some very large accelerators, while the sensors themselves or the data that they consume from sensors typically use less than a milliwatt when recording, when sensing whatever is to be sensed. Generally, the first component that the sensor communicates to after it produces data is a microcontroller. These sit in generally a power range of 1 to 10 milliwatts or so, but they're generally simple. They can't do very much in terms of feature extraction or machine learning or AI support at that point. And that's really where the chips that we're designing are meant to hit. So we're doing neuromorphics for the sensor edge, essentially. And how we've built the system that I will show to you in a bit is that for us, neuromorphic means a couple of things. So neuromorphic for us means heterogeneous. The analogy that I keep giving is if we take the brain as inspiration, then the brain has so many varied regions that are specialized for their tasks with varied neuron models and synapses, connectivity strategies, etc. So from my perspective, heterogeneous is neuromorphic. The other bit is that we do have an accelerator for what we call brain-like neural networks, but this is basically spiking neural networks. The chip that we've built is called Pulsar, that we're currently ramping up production for and will be available soon, is a microcontroller, a heterogeneous microcontroller that at its heart has a RISC-V typical CPU that does housekeeping and handles all the data movement and configuration of all of the different accelerators on chip. It comes with an array of different typical digital and analog interfaces. Like I said earlier, we're targeting a large variety of sensors, and they come with a large variety of different interfaces. Which then leads us to the data that would come from all of these interfaces would go to specialized components on chip, either, for example, FFT accelerators for doing operations in the frequency domain, a typical off-the-shelf CNN accelerator, so it would be possible for customers to come in, and if they already have a model that is a CNN or an ANN, they could already run it. maybe less efficiently than the alternative, which would be to use the spiking accelerators that we have on board, either the analog mixed signal or the digital SNN accelerators, coupled with the hardware encoders and decoders that make the conversion from multi-bit data to spikes very efficient. The kind of applications that we're looking for, so all of these sensors would be connected to our chip somehow. We're looking at a very large space of applications that fit in that power budget that I was showing earlier, the 1 to 10 milliwatts or even sub-milliwatt to 10 milliwatts power budget. So these are in the consumer space, the IoT and smart home, industrial, and wearables. For this presentation, I'm going to focus on radar specifically. So I'm going to introduce to you a product that our partner is creating. So Arrow Labs is creating a EAGLE. Is creating EAGLE, the smart smoke detector. This smart smoke detector isn't quite like the traditional smoke detector, so that you can find on the market at the moment. It has AI-based smoke identification. The use case for this is that you would be able to, for example, in hotels or resorts, you'd be able to tell whether someone is smoking or if there's a genuine fire, smoking, vaping, or if there's a genuine fire in the hotel room. It's also meant to have intrusion detection and air quality monitoring, but also human presence detection and people counting. This is the use case that we'll be focusing on today. And this one is really meant in situations where you'd want to be able to tell first responders really what are the hotspots in terms of people inside of a building, where are the people located, where should they prioritize searching and ensuring that they put out the fire. In order to get to any of these applications, we're sort of considering a typical time series processing flow. Typically, these are the steps that we've identified inside of a signal processing pipeline. They range from interfacing the sensor, conditioning the signal in some way, doing some feature extraction, doing spiking and coding, performing an inference on top of the spikes that you've produced, and then figuring out from the SNN what class of something are we looking at? What is the classification of the input? What are some features in the input? Programmable. So you get to choose the meaning of the outputs. So there are a few different paths that the signal and the data can take through the chip. That can take you either through more classical accelerators or take you through the SNN accelerators. And really, I'll show the rest of the stack as well, and then we can come back to this if we have time. We provide a software tooling called Talamo that enables a user, someone who ideally for us, or we target users who do not have neuromorphic experience. So a lot of the neuromorphic concepts, the idea of any particular network architectures that could be used that are more neuromorphic than traditional, or activation functions such as the are used typically in SNNs, they're hidden away, and we add tooling to make the training flow very simple by doing supervised learning in essentially PyTorch. We have to provide a lot of tooling though, so that was the high level, but in practice, what we provide from the PyTorch side comes with spike handling blocks, encoders, decoders, other different types of kernels, also for DSP. Then you also have to have the training ability, which I was talking about. But when you actually consider the deployment phase, you need to consider the quantization, any pruning that you need to do. You need to understand how you could debug a system such as this. Then we provide tooling that allows you to automatically or to produce code generation from a high-level Python representation of your signal processing pipeline to then be able to run either on a simulator or on real hardware using a suite of drivers that we've produced for the chip itself. So what we're really also trying to go for is, besides enabling a developer community, we're trying to produce essentially a vertical solution, a full vertical integration, which means that besides we provide customers with the chip and the SDK, but also with what we call an application architecture, which would mean the models that they could use for a particular task. So reference designs of how we've solved a particular task, for example, here, radar presence detection in the past, but also data capture and annotation tools, and a developer ecosystem that could support them and us and anyone else really in the community with developing solutions based off of SNNs. It's important to remember that us as a chip in the value chain, we might be the only chip in the system, meaning there's a sensor, the chip, and that's it. And our pulsar is responsible for taking an action. But in certain scenarios, if you produce a module, for example, then the pulsar would be integrating in a larger system that also has an application processor. So what we additionally do is we provide the APIs surrounding the pulsar-based module to be able to configure it and to be able to extract data in coherent ways. For example, if you have this system of a radar human presence detector or density estimator for crowds, it would be able to output the number of people, something about the characteristics of the people, for example, so if someone has fallen, and data capturing tools. And this is very important because, especially for radar, the community or the research community, but also in industrial senses, you can't really find data sets either for benchmarking or for any deployment scenarios. Really, the data sets are relatively small and quite specialized. So a tooling like this has to exist. So we provide an evaluation kit for developers to be able to start developing models and playing around with some sensors that we already provide, and get to know this little MCU. We also provide additionally or separately a radar-focused development kit that comes with a radar pre-built, pre-assembled, so that you can already start figuring out how to integrate this and how to use it. In order to get there, though, you need to have some data. So we provide experiment management and tracking. You set up your experiments ahead of time. You know what kind of data you need to record. And this is all a data-driven architecture. The data is king. We also provide support, tooling to be able to do multi-sensor recordings all aligned in time. So you'd be able to do radar plus camera plus time of flight, so that you can figure out what distance certain objects are and how to do segmentation better. Automatic or manual labeling, so you can use an automatic tool to label the objects that are in front of the RGB camera, and then you can go in and edit them if they're incorrect. But also additional visualizations of what the data looks like. If you're an expert, you can sort of figure out what you're looking for and if the radar is configured correctly or functioning in the way that you're expecting or not. The next step would be for you to take a model that you're training and then export it to a format that is embeddable. So my colleague Rafael talked about this last year at the EDGE AI event in Milano, where he was describing the application that he was working on IMU-based gesture recognition, to show how you can take a model that you've trained, a pipeline that you've trained and is purely in PyTorch, in Python, and then how you can lower it to a level that you can compile it and deploy it to a device. I'm not going to talk about this at the moment. I'm going to assume that I'm buying extra time by sending you to a different video. So I'm going to jump into what the application would look like. So this is the kind of deployment that we're expecting. It's essentially a radar mounted on a ceiling or in a downward-facing position. And the task is to classify the density of humans in the area around the radar. There's also there can be a lot of different adversarial situations for radars. The example that was shown just previously in the video showed a plant with a large rotating metal fan. These are adversarial situations for a radar, and we're showing here how how the radar plus a pulsar chip can do estimation of whether there's 0 people in front of the radar, 1 person, 2 to 3 people, or 3 plus or 4 plus. I'm not 100% sure. This is in order to get to this place, the neuromorphic advantage, the neuromorphic efficiency has to be present, as well as being able to train for models such as this. So I'm gonna end a bit early so we can have a conversation where the reason. So for us, this is the prime time of neuromorphics, meaning we are essentially ready for deployment and ready for large-scale developments for a few different reasons. We have the hardware platform that is flexible, and because we use SNNs, we can go relatively low in power or dynamic power, depending on the situations. We have the software toolset that allows you to train an entire signal processing pipeline with all of its individual components. So signal processing pipeline could be filter bank, trainable filter bank, encoder, SNN, and you can train parameters in each of those together to give you an optimized solution for a data set. Bring your data. The ecosystem that we're developing, so we have the developer program that I very briefly mentioned that will incorporate a lot of expertise into how Pulsar functions, but we also have solution partners that you can find a few on our YouTube channel. So these are companies that know how to design solutions based off of SNNs and how to train SNNs in PyTorch. We also have sensor partners, so we get a lot of intelligence on how to design solutions from the partners who provide us with the sensors. We're also focusing very much from a customer perspective on this vertical integration, where we do have radar domain-specific knowledge, but we've also developed a lot of tooling to accelerate this development from their side. So being able to provide them with a essentially model zoo of radar models that can then be adapted by them for their specific problem. And I think that's it for me.
Good stuff. I see a question from Spiridon you brought up there.
How seamless is the transition from a... Yeah? So how seamless is the transition from PyTorch trained model to deployment on your analog hardware? So depends on your definition of seamless. I think you have to stitch together a few blocks in Python, but it's basically all of it is integrated within this Talamo framework that I was mentioning. So it's essentially a sequence of a few different steps. One of it is defining what your pipeline is and then initializing it so it's untrained. Then training your model with whatever data set. And then it's a matter of performing a quantization step if you want to deploy to the analog mixed signal accelerator. This is handled by a specialized component inside of our toolchain that will output. So after you pass the mapper, that will output a description that is already configurable for the hardware. So you go ahead and use the drivers that we provide to configure the analog mixed signal accelerator with the weights that you've provided, and then passing data to it in the way that you've defined at the higher level, either directly spikes or using the hardware encoders to transform data to spikes.
Sense. Another one from Spiridon.
So what types of network architectures are currently supported on the analog core? So the connectivity patterns can be quite varied. It really depends what you're trying to do. The specific constraints are slightly more difficult to pin down because there exists for our accelerator, there exists a trade-off between how much input connectivity you have per cell, per unit, per neuron, and how many neurons you can actually have and support. So it's a bit difficult for me to to specify precisely numbers here, but in principle. So feed forward, fully connected, fine. Recurrent, fully connected, fine. Asterisk depends on how many units you're trying to connect. Wild, liquid state machine like liquid state machine network architecture is also fine.
Cool. And you also got a good there. So there you go.
Thank you for highlighting. Thank you, Marty.
Okay.
Yeah,
we have sound effects. Okay, so what's next on the hit parade here?
We have a very exciting talk from Jason Yik. Awesome. Hi, Jason.
Hello.
Are you ready to rumble?
Yes, let's go.
All right, we'll remove.
I'll stick around to let you know if the slides loaded correctly. Everything looks fine.
Great.
Take us away.
Thanks, Peter. Hi, everyone. I'm Jason. I'm a PhD candidate at the EDGE Computing Lab at Harvard Seas. And today I'm sharing with you a presentation on some recent research that we've been up to on optimizing neural networks for neuromorphic accelerator deployment. So this is related to if you've heard of the NeuroBench before, the benchmarking framework, this talk will be a sort of continuation or next step of work after NeuroBench. So I wanted to start by sharing with you a benchmarking maxim, which is what gets measured gets improved. And this can apply to anything in a benchmarking sense. But how does it get improved? Things get improved by learning what contributed to better performance. So if the idea is we have some neuromorphic chips or neuromorphic accelerators, by benchmarking them, we'll learn what did cause our accelerators to perform better or worse. And that's going to lead us towards further improvement. So of course, we've heard about all types of bio-inspired or neuromorphic computing across the stack for today, spanning from at the low level device technology and circuits, through accelerator architectures, neural network models, and up to learning and representations. Today, I'm going to focus on these inner two, the accelerator architectures characterized by a high degree of parallelism, message passing, and this co-located compute and memory, or as John Tapson was saying earlier, these compute in memory type of architecture, as well as the neural network models that go on to these accelerators, featuring things like spiking neurons, multi-compartment computation, and recurrence. So to iterate on the technology for this talk, the algorithms we're looking at are things like spiking and recurrent neural networks, which emphasize sparsity. And the accelerators that we're going to look like are the accelerators which are most available for research today, which are these compute and memory many core SRAM types of accelerators, including Intel's Loihi, the brain chip, as well as chips from Synsense. So when we have these algorithms and accelerators under study from neuromorphic research, the natural question is, how should we co-design systems to maximize our performance when we put the algorithms onto the accelerators? And this is an especially interesting problem in this space because if we take a look at the conventional accelerator space with things like GPUs, there is this off-the-shelf availability where you can go and everyone can own a GPU. And when you're developing your algorithm or say your neural network and putting it onto that GPU accelerator, you'll be able to execute that, get some real world performance, and this is going to directly inform your research about how well your algorithm performed. In this neuromorphic space, there is building availability and under-researched topics for both algorithms and accelerators. So this kind of splits the space of algorithms and accelerators. If you were a neuromorphic algorithm developer, you would think you would not easily be able to take your algorithm, go and deploy it, and be informed by whatever real-world performance you got in the same way that you can do with a GPU. So how should we bridge this gap between the algorithms and the accelerators? And this is the topic of my talk today. We can bridge this gap by performance modeling from accelerators to inform our algorithmic complexity metrics, to inform what a model of whether the algorithm would have performed better if we had deployed it in the real accelerator. And from this performance model, we build a bridge between the accelerators and the algorithms, which lets us co-design between them. So here's a quick outline for what I'll be talking about. First, I'll be talking about the algorithm sides of things, starting with algorithmic benchmarking. Then I'll talk about some recent work we have in accelerator performance modeling, which starts to bridge between the accelerators and algorithmic metrics, which can predict the performance of how an algorithm might do. And then I'll touch on how we can start to co-design between the algorithms and accelerators that we have. So first, we can talk about some algorithmic benchmarking, and this is where the NeuroBranch project comes in. So I've been talking about algorithms, and we've heard a bit about this in previous talks today, but I'll put an example of what people might refer to when they say neuromorphic algorithm on the screen now. So this is a spiking neural network, or a representation of a spiking neural network. It contains these stateful neurons, which are charging over time, hitting some threshold, and then firing. And based on the neurons which fire, we can start to make predictions, and that can be useful for machine learning. Why would we want to use spiking neural networks? Like we've heard before today, spiking neural networks or neuromorphic algorithms which have these types of features feature this high dynamic sparsity and this constant memory footprint, which is not growing over time. And both of these things can lead towards efficient computing, which will be useful in efficient ML. So here are some other algorithmic approaches for efficient ML. Things like dynamic sparsity. And note that not all of these are commonly called neuromorphic, but these are general approaches which can be useful across anytime you want to do efficient machine learning. So for dynamic sparsity, we have things like sparse transformer attention, introduction of ReLU in order to add sparsity, and these mixture of experts. And then in terms of memory footprints, constant or low memory footprint has come before in the form of weight pruning, or things like linear attention from things like state space models or SSMs. And there are many more of these approaches across research. And now we have these efficient ML techniques, which in theory can help us to assess the performance and efficiency of our algorithms. But how to assess performance? Because recall, the accelerators specialized for these features are under active research and not widely available. So the action taken from this algorithmic front is to centralize on complexity metrics as performance indicators. And what this necessitates is a common framework for standard measurement, so that if one researcher comes up with some type of approach, then another researcher can come up with their own approach, and those two go head to head under this common framework, are standard, have standard measurements one against the other. And then we'll be able to learn what features of one made it better than the other. So this common framework is the goal of the NeuroBench project. So Neurobench is this benchmark framework for neuromorphic computing. Restating the goal, Neurobench aims to have these standard tasks, evaluation metrics, and software for benchmarking neuromorphic algorithms. And the approach we took to design Neurobench was to engage the community for collaborative design and importantly, emphasize extensibility so that the tool could continually expand in the future. And we were very lucky to have very many participants interested and willing to help in bringing up this common benchmark tool. So from the Neurobench, there are various algorithm benchmarks as well as common metrics which can be used. So on the task or application side, Neurobench has built-in support for these types of tasks, including keyword, continual learning, event camera object detection, motor neural decoding, chaotic sequence prediction, and human activity recognition. Like I said, it's important to emphasize the extensibility of the Neurobench tool. So the applications you see on the screen are not necessarily the applications that Neurobench is limited to. These are the ones that are currently built now. Over on the metric side, not only are we measuring that first-class metric of accuracy, if your network or if your algorithm is not accurate, then it is hardly useful in deployment. But we're also considering as first-class metrics complexity metrics or cost metrics, which can entail how efficient your algorithm was. So that includes things like your memory footprint, your connection and activation sparsity, counts of synaptic operations, as well as things like number of neuron updates. And so the framework reiterating necessitates this common tool. So the Neurobench algorithm benchmarks have this common PyTorch-based tool, which anybody can go and download. It's completely open source. With this tool, we presented some baseline algorithms, including things like ReLU networks, SNNs, LSTMs, echo state networks, etc. And we included all of these examples into this common PyTorch compatible software framework, which you can get easily with a pip install Neurobench. Some initial findings from the benchmarking we did to start with Neurobench was that quantifying the algorithm cost benefits and usually the accuracy trade-offs. So I'll put an example on the screen of some of the example benchmarking that you can do with Neurobench. So Neurobench, to start, featured these two baselines. And so this is for the neural decoding task. Our accuracy metric is this R squared. And in addition, we have the further complexity metrics of footprints as well as synapse. And so you can see in our baselines, we were able to achieve this spiking neural network with slightly improved accuracy over our ANN baseline at the cost of perhaps some memory footprints, as well as dense synapse. Dense synapse here refers to if you had no support for zero skipping in your computation, this is how much it would cost to compute. But what you can note from the SNN baseline is that if we go to the effective synapse, effective max or effective accumulates, which you would be able to achieve from a hardware backend that could skip zero synapse, you can see that the SNN baseline is much more efficient in terms of its compute compared to the ANN baseline. So those are our two baselines which we shipped with that version 1.0 of Neurobench. But then what I'm showing in these lines below are further research, further algorithms developed at the IEEE BioCAS Grand Challenge, submitted by teams around the world, which aim to improve on the baselines for this particular task. So I've highlighted here this one, the recurrent SNN, small, where you can see compared to the baseline we were able to achieve, they achieved far higher, or you could say higher, accuracy in that R squared at a similar amount of memory usage and a similar amount of effective synapse. So you can see how by measuring these different types of approaches that we have, we can start to track the progress over time of algorithmic improvement. All right, so that is on the algorithmic front. I just talked about the Neurobench tool for benchmarking algorithms. And now we'll start to move into the accelerator world with accelerator performance modeling. So the architectures that we have with neuromorphic chips nowadays support this dynamic sparsity with asynchronous message passing, and we have this fully memory on chip execution. And here is a abstraction of what your neuromorphic type of accelerator might look like. So at the macro level, you have these tiles, which are neurocores, and the neurocores are connected to each other via a network on chip. Within each neurocore, there is a pipeline for operating your neural network compute flow. So that includes whatever messages you get, the weights that these are multiplied by, the computation, as well as the unit to send out the activations to the other neurocores. And the compute flow that this ends up being is that with these current accelerators, we have this discrete time type of flow, where at time step t, you accumulate your synapse, multiply them in order to produce your activations, and send out your activations before barrier syncing in order to move towards the next discrete time step. So going through each of these, you can note the places that we have supports for things like sparsity. So by having this synaptic weight memory nearby to your compute, we have this static sparsity or static weight sparsity supports. With the activation messages out, which go on the network on chip, we have this dynamic activation sparsity supports. And the most unique accelerator attribute that I wanted to add here is this compute in memory notion, that there's this static neuron and weight allocation with each of these neurocores. The weights are not moved around the chip. So with Neurobench and in some of the talks we've heard from, we hear about these standard algorithmic cost metrics, which are things like sparsity ratios and the number of synaptic operations that the network performs. But when we take a look at this accelerator architecture, we can ask, are these really good performance proxies? Like, if we know what sparsity we had, can we tell from the accelerator where our performance is going to be improved? And asking this question really moves us from the algorithm world into the accelerator world. And so restating the question, as we start to take a look at accelerators, the question becomes, how do I develop my algorithm in order to ensure that the deployed performance is going to be strong? I'll speed up a little bit. I think I'm running a little bit low on time. So in classic architectures, you might be familiar with this roofline model. And the roofline model will look like this, where the main thing that it's capturing is the fact that off-chip memory access is very expensive. And off-chip memory access is defining this bandwidth bound of the roofline. And so you can have your different applications, which are going to be on this performance slope. And wherever you land along this roofline can tell you where your performance can be improved for this conventional backend. But the roofline doesn't work for this architecture that we're looking at because there's no off-chip memory access. So what matters when the memory wall is not there? Things that can affect accelerator speed include weight sparsity, activation sparsity, as well as partitioning, how you decide to take the network and then parallelize it across the cores. And what we did in our research work is to do some real system evaluation. So we took a real network, a trained network, and then we swept through different levels of sparsity and different levels of partitioning. I'm going to have to speed through some of these results because of time. So the first thing we can note is that sparsity imbalance can cause your performance to act in a way which is not expected. So if we have balanced sparsity, if we put the sparsity uniformly across the network, you can see that as we increase sparsity, our performance is going to improve linearly. But if we start to imbalance the sparsity in different ways, our performance no longer necessarily is as connected to the sparsity that we're getting. And this tells us that the network level sparsity is not very good as a performance proxy. So what could be a better performance proxy? Well, let's find a better x-axis to put all of these points on. The better x-axis we can put all of the points on is some notion of synapse. So changing the x-axis of those points from sparsity to the max synapse, which is going to tell us which is the slowest neurocore, gives us a much cleaner performance model. What we're looking at here is that on the x-axis, we have the maximum synaptic operations of any neurocore that is active. And we have y-axis is our performance. And you can see this very clean linear relationship between these two things in a way that starts to resemble the roofline. You can do things like analyze the floor, which this roofline or this type of graph ends at. So the floor can move down and down based on the amount of neuron computes. And you can also look at configurations where the algorithm doesn't necessarily match onto this floor line bound here, and the points start to rise. In other words, the performance is worse than what the boundary is showing. And this can be because you have traffic bottlenecks on your chip. So putting this all together, I'm sorry that I went through quickly. Putting this all together, we can start to determine what is actually important for performance when we look at this type of compute and memory architecture. We can have this slope, which is memory bound, and that is determined by the access latency. And moving along this slope involves increasing your weight sparsity, increasing your message sparsity, and your partitioning. And we can have points which are not on this memory bound slope and, for example, rise above it. And these are your traffic bound points. And in order to improve our traffic bound points, in order to move these downwards towards the performance bounds, we can do things like increase the sparsity, go for a better mapping, or actually reduce the partitioning via coagulation. Finally, once the memory accesses or synapses are no longer what are bottlenecking us, and we start to reach this compute bound, we can start to looking towards partitioning of the compute bound in order to improve the performance there. So how can this floor line model be used? Like the roofline model, a network which you deploy to the accelerator will land somewhere on this graph. And based on where it lands, you can make a decision about how you're going to optimize it in order to move it towards towards getting higher performance. So from a naive baseline, which can be at some normalized performance 1.0, we can use the performance model here and track the floor line slope going down and down. Across these different iterations, we're moving down this slope here. And where we end up with is at a performance which is twice as good as the naive baseline. So through this performance model, the floor line performance model, we have connected algorithms and accelerators. And the findings are that network-wide sparsity metrics or up counts don't capture the parallel deployment across these accelerators. The performance is highly dependent on how you partition the network and then deploy it across those compute and memory cores. And the synapse per neurocore indicates what is your usual bottleneck. So this is how we have connected via a performance model from the accelerator world up to the algorithm world. The final step in order to close the loop across the system co-design, if this performance model is showing what currently matters for system performance, the question is, how should we co-design our next generation of neuromorphic algorithms and accelerators together such that the performance entirely can be improved? Like I said, I know I went through this quickly, so I'll direct you to further reading. We have a preprint with all of the plots in more detail, as well as more explanation of all of the methods up on archive. You can find it here. And that's where I'll end my talk for today. Thank you, everyone.
Thank you, Jason. This was very, very interesting and thought-provoking. I do always have a bit of a question when it comes to dynamic sparsity versus dense. Like, what kind of assumptions are being made when it comes to the cost in terms of hardware and the cost in terms of energy, whatever you want, to support the sparsity rather than just going dense. You know what I mean? What is the design trade-off there? I don't know if you have any thoughts about this.
So dynamic sparsity can be realized in multiple ways. The way that these compute and memory types of systems realize dynamic sparsity is by reducing the amount of messages communicated along the NOC. And this is common across a lot of these neuromorphic types of designs. Another way that you could have dynamic sparsity is the MOE type of approach, which is used by GPU accelerators. And there, the dynamic sparsity of choosing which experts involves whether or not you load the expert weights from your memory into your GPU accelerator. And so in that way, it is the same thing as reducing communication, but it appears very different because in the GPU world, the MOE is helping them to load fewer weights. In the activation sparsity world, or neural network activation sparsity world used by neuromorphics, activation sparsity is helping you to route fewer messages. This is important because the way that you achieve dynamic sparsity can affect your performance or how much performance you can get from a particular accelerator. So for example, the MOE strategy is hard to imagine with this message routing system, because if you choose the expert, you'll need to know where to compute. So it is not necessarily that you're moving fewer messages. In every token, there's going to be the same number of experts. And if your messages are all moving on chip, then it's not very clear how that will help. I'm not sure if I explained that perfectly well.
No, I think you did, but I think that to some extent, in this edge AI space, let's say, or in the ML versus traditional ML versus neuromorphic context, there's always a conversation of I can build a model that is an ANN or CNN or whatever, and it's traditional, and doesn't exploit any activation sparsity, versus a model that you have to, ignoring the retraining and or any transformations that you need to do to a model to make it have more activation sparsity, or in a neuromorphic sense where your neuron doesn't spike. How much more complex does your hardware have to be, to be able to deal with one versus the other? But I think I understand your point from the algorithmic perspective, and also for workloads that are better understood, I think, than neuromorphic versus traditional. Okay. Thanks a lot, Jason.
Thanks for having me.
Sorry?
Thanks for having me.
Our pleasure. Rosina, Matthew's not meant to be on. I think we're looking for Jason Nishlagian, if he's ready to go. I'm not prepared to do a song and dance. Don't leave me up here.
Yeah, unfortunately, he's not here. I don't know why, to be honest.
Uh-oh.
So I will have to ping him and we'll see. Yeah, I'm sorry because I thought, Jason.
But Jason,
get him on.
Jason was here earlier at the test phase, yes?
Yeah. So
probably having some technical difficulties.
Probably, yes. So, yeah, he was here earlier. So who's left on our agenda? We got talks, or
it's just Jason.
Wow, okay.
It's just Jason.
Well, maybe folks have some extra questions in the chat here while we're finding Jason. So far, so good, I think. Let's see. Here for some extra interesting questions. So just to reiterate, we are recording this. It is going to be on our YouTube channel. If you go to youtube.com/@EDGE Foundation, you'll see this. And actually, we have a whole bunch of talks on there. So every other week, we do a live stream called EDGE AI Talks. We have lots of different folks on there that are doing kind of engineering explanations of their stuff. Some of them are professionals, some of them are PhD students. But so when you go to the YouTube channel to look at this, you can also browse that as well. Another thing we have is if you are into podcasts, we have the EDGE AI Pod, which is like an audio version of a lot of this stuff. You can subscribe to it on iTunes and Spotify. Just look up at EDGE AI Pod. That's another way of kind of getting this stuff on a regular basis. I think we publish a new episode every week. So that's pretty cool too. And I would say in my promotional stuff here, I will also reiterate EDGE AI San Diego QR code is there. And you can go to this URL, San Diego 2026 at edgeaifoundation.org, and reserve your seat. We actually have special discounts for academia. So if you're a student or educator, yeah, super good price. If you're from some multi-billion-dollar big tech company, you have to pay full price. That's just the way it works. So, but we do have some seats available still, and that's going to be happening March 24th to the 26th. Like I said, 15 hours hands-on workshops. We're going to be actually live streaming one of the workshops. But we'll have other workshops from lots of different partners down there. Demos, kind of an expo area, panel discussions, things like that too. And then we have an evening reception on the deck of the USS Midway, which is a big aircraft carrier. So someone asked me if that boat moves, and no, it does not. So we'll not be cruising around San Diego Harbor with an aircraft carrier. But we will be on the aircraft carrier, just kind of hanging out. So that'd be fun. So that's happening. What else is happening that's coming up? For those that'll be at Embedded World, we will be there. We have like about 31 partners there. I know Inatera will be there in force, right? Showing off all your cool stuff. BrainChip will be there. You saw them talk today. So that's really good. And in Nuremberg. And here's Jason. Excellent. You can stop talking again. Okay. Let me pull this down.
Hey, Jason.
Hey, how you doing?
All right.
Okay,
So
how are you?
just getting started here.
Doing well. Do you want me to go ahead and just kind of share my screen now?
Share a screen and we'll kick it in.
Beautiful.
All good, all good. And you are connected in from Santa Cruz, California. Is that
You got it.
awesome?
Our first day of sun in a little while.
Nice. A little sun is a good thing. All right, I will retreat and let you guys have the floor.
Thank you, Peter.
Okay, am I assuming we're good to go?
You are good to go.
Amazing.
Whenever you're ready. We can see your slides. They might even function.
Perfect. Okay, so I'm going to do a quick dive of some of our wins and failures with neuromorphic language models and give you a sense of how we started our work in building out larger scale systems with neuromorphic computing and where I think a valuable direction is to go in. Now, I'm not going to go into the low level neuronal components in much detail. I feel like that's probably part and parcel of this whole session. But if we assume that a spiking neural network, which is very synonymous with what neuromorphic computing is about, is defined by features like reduced memory accesses and sparsity and things that and recurrent dynamics, then the leaky integrate and fine neuron is a very simplistic way to view that. And if you were to probe the internal dynamics of that neuron, then you might see a membrane potential that evolves something like this. That's as far as I'm going to go on that, so that I can go into larger scale setups. But I would say about half a decade ago now, I started working on SNN Torch, which enabled gradient-based learning with spiking neural networks. And I think in 2026, it doesn't matter so much now, right? There's a lot of tools that enable you to train spiking neural networks with reasonable efficiency, piggybacking off a lot of modern existing tool chains, namely PyTorch. But this managed to get a little bit of traction, so it seems to do a good job for a lot of people in onboarding them into the spiking neural network realm. A few companies and places have used it in their own work, which is kind of nice. We started working with SNN Torch on small scale problems, and then figured out ways to scale this up into more challenging domains. And what I'm showing you here is just a very extensive set of tutorials that let people get onboarded into using it if that's what you care about. So with that being said, we wanted to target large scale problems. And before I give you those large scale problems, I'm going to give you a very stupid sentence, right? That sentence is Shrek saw Taylor with binoculars. And my question to you is, who has the binoculars? Is it Shrek? Is it Taylor? Why do we care? Now, linguistically speaking, this is ambiguous. This sentence is ambiguous by design. You could couple binoculars to Taylor. You could couple binoculars to Shrek. But given that we're humans with a bit of context, we're able to make some level of logical deduction, we could probably infer that Shrek saw somebody else. Therefore, Shrek is the one with the binoculars. Why am I giving you this sentence? Because I want to give you an illustrative example of a case where the modern approach to large-scale systems, large-scale language models, has benefits and has drawbacks. But you break down this sentence into tokens, and I'm just going to represent it with words, and each of these gets expressed as a vector that goes through quite a sizable number of operations in order to parse a sentence such as this. At some point in your language model, you're going to end up with what's known as an attention matrix. And the purpose of this attention matrix is really to just find correlations between each word in the sentence, or each token in the sentence, and every other token in the sentence. So in this very simplistic example, maybe your first layer lights up significantly at the link between Shrek and binoculars, right? Lighting up, implying that there's a large number, there's a large attention score. So that's all well and good, but you could probably appreciate that if I started throwing in PDF files and really long sequences to my model, then I'm going to add an extra item along my x-axis, and in a naive implementation of this, an extra item along my y-axis. So you're kind of storing everything with perfect memory, right? Beyond perfect memory, your memory is growing quadratically as your sequence length increases. And I think it's safe to say that you are not storing every single word or syllable that I'm saying right now, right? Your brains aren't undergoing neurogenesis with every word I say. You're really just extracting some kind of high-level meaning and taking away your own interpretation of what I say. That's how humans work, right? Now, if I was to take a leaky integrate and fine neuron or a recurrent neuron, something with dynamics, something which does not have an expanding state over time. An evolving state, sure, but not an expanding state that needs to allocate additional memory. Then the risk that I run there is that by the time I've reached the end of my sentence, I have this issue where a lot of that context about Shrek may have been superseded by Taylor. And if I overlay the leaky integrate and fine neuron, maybe the first spike represents Shrek, and then this influx of subsequent spikes represents Taylor with binoculars, or a very, very toy example. But you can see that all contextual information about Shrek has effectively decayed. It's faded away by the time we reach the word we care about, binoculars. So there's this kind of a tug of war here, right? Because with attention, you have too much information, but it works really damn well. Whereas with spiking neural nets, and more generally recurrent neural nets, and a lot of things that people characterize as neuromorphic, they're cheap, but naively, they don't have enough information. So we spent a considerable amount of time trying to bridge this gap. And of course, there is perhaps a limit on how well you can do if you're not going to just allocate quadratically scaling memory. But the point is, we have a decent enough blueprint in the brain that gives us promise that you can do something pretty solid. So let's aim for something that reaches usefulness, right? The first thing that we tried was Spike GPT. It was the largest spiking neural net trained via backprop at the time when we released this in 2023, and it was the first of its sort to perform language generation. It was the headline was 30x less operations than a transformer of equal size. And if I can be completely candid with you here, the model sizes that we tested, one was 216 million parameters. You can appreciate that that is approximately 10,000 times smaller than our modern trillion parameter scale language models. We did go ahead and push that further. We tested out a 1 billion parameter model, which I think a lot of folk consider as that kind of threshold, that critical threshold of actually moving into usefulness. But how did it go? Why isn't the world using Spike GPT if this red text is all it's cracked up to be? The reality was that scaling hurt. Maybe it's the training difficulties of SNNs. Maybe it's just that we were compressing a ton of activations into a binary space. That hurts, right? We do have these theories that spiking neural nets are encoding information over time. But I think the reality is that there's still a lot of research to do there in order to really extract the value of time. Because really what's happening in this specific model is just pure kind of gross compression, right? Zeros and ones. The scaling issue was that, as you go from a 216 million to a 1 billion parameter model, it didn't really follow the same scaling trajectories that non-spiking neural networks were undergoing. So a few lessons learned there, right? It was cool that we did it, tied that up into a nice bow, and then took our learnings to an alternative model. And that is this matrix multiply free language model. Let me give you a bit of context on what that is, just verbally for now. It's a state space model, right? It falls under the class of linear recurrent models, which is very, very similar to what spiking neural networks do. So this is stateful, it's recurrent, it follows the same sort of dynamics as all of your vanilla spiking neural networks out there. We do draw upon all of the peripheral layers and components of a regular transformer block, just without that painful quadratically scaling layer. We introduced a couple of features to enable it to be matrix multiply free. One of those being ternary weights in your dense layers, right? Because 1 times some input is just the input. 0 times an input kills your input. -1 times your input is a bit flip +1 in 2's complement. So, computer scientists might hate it, but chip designers should comfortably accept that you can get rid of matrix multiplication and replace it with some sort of multiplexer in any sort of vector matrix arithmetic. So all of that was well and good. We introduced these ternary parameters, which kind of not only remove matrix multiply, but I guess more importantly, reduce the memory overhead. And of course, if you're going to avoid expanding the amount of memory you allocate to your model as your sequence length grows, then you need to forget something, right? You can't just keep adding memory without discarding something, and we know that brains prune information that doesn't seem very salient. So we took heavy inspiration from LSTMs, and I guess we just linearized all of that to make this far more effective to train at scale. And this number is outdated now. We've been able to do a much better implementation on Loihi 2 within 2 watts. And this is across a multi-die system. So let's talk about that hardware for a moment. I'm going to show you a few different results and a few different learnings. The first thing that I want to show you isn't actually very impressive whatsoever. On the x-axis, we have the sequence length, right? On the y-axis, we have throughput in the number of samples or tokens or words generated in 1 second. In blue, we have our matrix multiply free language model. And in all the other colors, we have kind of your base transformer plus model, which is more or less the backbone of all open source models. At these small parameter scales, it's quite representative of anything that relies on multi-head attention. So Llama, QN, and so on. How do we do? Well, higher is better, right? We want higher throughput. And we're seeing that at low sequence lengths, this blue line isn't doing very good, right? Okay, that's a bit of a bummer, but it does make sense that as your sequence length grows out, that's the case where this quadratic scaling of transformers hurts. So that indicates that maybe our chance to shine is in the longer sequence length regime. And to be fair, 1,000 tokens isn't considered long sequences anymore. So that's fine. Well, what are we missing from this picture? Energy, right? Energy is what we're missing. Now, transformers can't be deployed on Loihi very effortlessly. It's not an architecture that makes sense, given its continuously expanding memory size. Matmore-free does make sense. And so we do this kind of, we attempt to do an apples to apples comparison in the single batch regime with a Jetson Orin as against the Intel Loihi 2. Before we go there, I just want to make it clear that it was a very non-trivial engineering effort to map this model to neuromorphic hardware. It's non-trivial because effectively we have to define how to allocate cores, how to allocate everything to every layer, and how to map data movement between all of these rather heterogeneous operations. Having said that, much of these operations are maybe a tiny stone's throw away from what spiking neural networks do, what linear recurrent networks do. So it was possible, right? The point is that it's possible, and it's given us a fair bit of a good idea on what direction things might need to take. What I think is the most interesting thing about this, though, is that language models are generally running in two primary operation modes. There is autoregression, aka decoding, and that is the case actually. And there is also this other case of prefill. In prefill, you can visualize it as you've typed into your chat window with ChatGPT. You've got a long sequence, and then you hit enter. The goal is, given an arbitrary input sequence, predict the next token, right? That's prefill. You're prefilling your pipeline or your context with a ton of different tokens in parallel. Once you've generated the first new token, you kind of loop that back around, and you want to generate the next token to keep generating a stream of words and padding out your PDF files or whatever. In that latter case, you only have one new token, and you need to generate the next token given that one new token. That's autoregression. That's decode, right? So with prefill, you have a ton of tokens all in parallel that can fill up. And if you implement this using pipeline parallelism, then you can fill up you've constantly got every chip activated. Okay, wonderful. In autoregression or decode, you've just got one token that is passing through this these multiple layers. So really, only one layer is active at any given time. That meant that there were different trade-offs and different benefits that you could derive depending on what you optimized for. And these were active design decisions that we had to make. So one of our findings was that in large-scale systems, activation sparsity really only helps with the prefill case or when you're serving many users, right? When each of those input tokens is independent of one another, that's when all of these chips are active. And so if you have activation sparsity, then each of these chips wins from that. On the other hand, if I did activation sparsity, if I made these networks infrequently active, then the only thing that it's going to help is one of these many, many chips, right? And in the 1 billion parameter case, you're using something like 12 chips. So dynamic power is not very dominant here, really. It's static power that's killing you. And activation sparsity doesn't help static power. So how can we address that? Well, that's where weight sparsity comes into play. If you're able to inject a good degree of weight sparsity, then you can compress the amount of chips that you need by mapping multiple layers to a single core. Not to a single core, rather to a single chip. That way, the amount of energy that your SRAM burns significantly drops, and that's the primary issue. Leakage is the primary issue in the autoregression or decoding phase. So that is a design decision that needs to be made. And if I can show you the results with respect to energy, it looks something like this. On the x-axis, we have joules per token, the amount of energy it takes to generate one token. And on the y-axis, you have throughput per watt. How many tokens can you generate given 1 watt of power? And in green, we see the baseline transformer plus values that we want to beat. And of course, low energy with high throughput in this top left quadrant is where we want to sit. And if you can bear with my VC pitch deck for a moment, this is where matmul3 sits. And we have to account for the fact that these Transformer++ models are using BrainFloat 16 numerical formats, while the matmul3 relies on ternary. And so matmul3 uses less memory, denoted by these smaller circles. And as far as the short context, up to 1,000 context window benchmarks go, it works just as well as Transformer++. Full disclosure, state space models tend to break down a little bit in the exceedingly long context benchmarks. And when you have to do recall there, that people have kind of been able to use hybrid models and combine state space models such as matmul3 with regular transformers to really elevate performance beyond the sum of the individual parts. So with that being said, if you want to aim for state of the art here, hybrid models are one way to go, and that's quite well established now. But on the other hand, one thing that we recently looked at were looped language models. So rather than segregating out the transformers and the state space models and just maybe you make 80% of your model a linear recurrent model inspired by spiking neural nets, and then a little bit of your model a transformer. What if you applied dynamics? What if you applied recurrence to your transformer? Right? And so this leads me on to this final depiction of the latest model that we dropped back just in October of last year. And it's done the rounds. It's for good reason as well, because this is where we've really hit state of the art at the 2.6 billion parameter regime. And we're doing latent reasoning using looped language models, which introduces this sort of recursion. Imagine an input token going into a layer and into a sequence of layers. A regular transformer would just generate an output token. But with this looped language model case, you have this execute that says, that decides, is the answer that I've got good enough? If yes, fantastic, I can terminate. If not, let me loop around a little bit. Let me think a little while before generating the next output token. Right? And so the data flow looks something like this. And then suddenly, even though this is relying on a transformer, you're injecting weight reuse again and again. And that is something that feels very neuromorphic. That's something that I think that people working on data flow style chips have become very comfortable with. So with that being said, I hope you have a sense of where reasoning might be going, taking advantage of recurrent dynamics that we wouldn't have come across. We wouldn't have developed this model had it not been for all the work that we did in the spiking neural network, work, I guess. So with that being said, none of this is possible without the absolute stars of my lab. And in particular, a lot of the language modeling work was done by Bridger over here. So with that being said, I'm happy to wrap up and I don't know, take a break.
It's Jason, thank you very much. It's not time yet to take a break. Because I'll probably ask you some questions, and I'm also waiting for the community to ask some questions online, but I can ask some of mine. We had a presentation from Hector earlier today talking about spin cloud. You're talking about large-scale LLMs. Is it now the time that everyone should adopt a neuromorphic LLM, or is it okay to still build a few nuclear power plants?
So the thing is that you could even use nuclear power plants to build out neuromorphic language models, right? It's just the point here is that you can still operate in the high power regime using these neuromorphic inspired techniques, which involves recurrence and dynamics and all that. It's just that we want to, if you can do better with less, how about we scale that up and do even better with more, right? That's kind of been our mantra in this line of work. And I didn't really express the scales at which we were operating for the latter models. We trained on 7.7 trillion tokens, which is basically industrial scale. That's competing with Gemma, QN, Llama, all those guys. And we found that those models were doing 3 to 5x better than models that are 3 to 5 times larger. So all that is to say is that we are generating insight into ways that let you do far more with, I don't know, your larger models, right?
Just for scale, what was the scale of these models that you're describing now at the last one?
Yep. So the parameter size was approximately 1.3 to 2.7 billion parameters. The data set size on the last model, the latent reasoning looped language model, 7.7 trillion tokens. Though with matmul3, that was a far smaller scale. The same parameter sizes, but 100 billion tokens.
Would you say, I mean, you're making some empirical observations about the performance of these models compared to more traditional approaches. Can you make any prediction about, you know, the host of this for the host of this presentations of the EDGE AI Foundation? How does it start looking once you boil these networks down to a few million? Less than a few million. How do the performance benefits scale?
How do we bet? So let me generalize your question a little bit to start with and say, how do we benefit the edge, right? I think it's safe to say that we are at a point where, you know, you can deploy models that are on the low billion, single-digit billion parameter scales at the edge. I mean, iPhones have them, so there's no contention there. With the looped language modeling case, that generated a ton of insight for us. It was basically enhancing parameter efficiency. So if you're looping, then there's a couple things that you might be. With a language model, there are a few vectors along which you might want to improve your models. One might be, let's enhance our model's ability to memorize and remember and recall information. Another vector might be, I want my model to be able to manipulate information. I want it to, quote unquote, do reasoning a little bit better. So how does looping help something like that? We did a slew of tests across a very wide range of parameters, down from tens of thousands of parameters, very tiny, up to the billion parameter regime, to see what it was that looping helped with, see what it was that recurrence helped with. And this was inspired by the work from Meta, based on the physics of language models. They generate a bunch of synthetic data sets. For memory retrieval recall, the data set that they synthesized was just a series of biographical information. You train a language model only on that information and a ton of biographical data, and then you start probing about those biographical facts. In our case, with the looped language model, no benefit. That wasn't surprising because we're not adding parameters, right? But then on the other hand, we were testing out data manipulation capabilities as well. So what is data manipulation? Let me give you a silly example. Okay, so perhaps memory recall is what month was Jason, was I born in? July, right? Data manipulation might take it one step further and assume you can do recall and say, is the date of Jason's birthday even or odd, right? In my case, it's odd. So you have to operate on something that you've stored. Now, let's generalize and call that data manipulation. That's what looped language models helped with. That's what we saw as we added extra loops. Then you were jacking up the performance somewhat exponentially up to a limit, of course. But that's where all the gains were coming from. So the point is that, and we observed this across all the parameter regimes that we tested, 10,000, is that optimal for language? Probably not, up until the billion parameter regime. So really doing extra computation by looping made a lot of sense if you wanted to increase your performance on knowledge-based tasks, on data manipulation, given a rather finite set of weights. If you don't have the memory to expand the size of your model, that is the thing that makes the most sense at the moment, I think. It feels kind of neuromorphic because, I don't know, our brains just loop until we die, right? It's just an endless loop rather than 4x loops.
Okay, very well. I think one of the other questions that I had... okay. Hector, coming in with the question.
Yeah. So I'll summarize that if you'd like. What's an optimal hardware architecture for ternary-based models? Things were, proud of what we did on Loihi, but some of the implementation choices might have constrained the model. Yeah. This is totally fair because Loihi was only really optimized, Loihi 2 at least, was optimized for 8-bit int and 16-bit int. So we couldn't stick with ternary parameters on that. There's going to be a ton of redundancy unless you intelligently pack together a bunch of ternary weights, and I don't think that made too much sense on Loihi. So ternary on digital accelerators doesn't make a huge amount of sense unless you completely change the memory cells that you're using. There has been a little bit of exploration into using ternary weights on, I guess, your tri-cell or tri-level memory cells, flash, RAM, etc. Then that does go down the road of analog style in-memory compute, which is I consider that somewhat exploratory. I'm happy for others to correct me, of course, if it's not if it's gone beyond that. Quite frankly, in today's day and age of digital dominating a lot of technologies, perhaps it makes a fair bit more sense to say that maybe we should just bump it up to 2 bits, right? In fact, from an algorithmic standpoint, the physics of LLM work asserts that every parameter in a language model, at least, seems to store approximately 2.2 bits of information. So maybe ternary is just, ternary still works. It's still a good number because it's quite close to 2.2, but there's no harm in bumping it up and relaxing the matrix multiply free branding and just going with 2 to 3 bits, right? If I want to build something that really works, that is going to take over, that's where I would go. I would just increase my precision just a little bit. Otherwise, the hardware architecture question, don't have a really concrete answer for you other than things that worked and things that didn't work.
I have one additional question that isn't listed, and it's my own. Jonathan Tapson earlier was talking about looking at Hugging Face and looking for models that have spiking in the title. I'm wondering what it feels like to you. What is your perspective on like the avenue where neuromorphs publish LLMs? Is the rate of publishing of spiking or neuromorphic LLMs increasing, decreasing, staying kind of the same over this past kind of year? Do you feel like Hugging Face is the right place, or are we missing something?
There's a fair bit to unpack there. Okay, so what's the trajectory of spiking language models in, let's say, in research, because that's where most of it seems to be taking place. Of course, it's been increasing, but if I can be completely blunt, I do feel like a lot of it is increasing in the wrong direction. I see a lot of papers that take spiking plus self-attention and say, bam, spiking transformers. And the problem with that is that you're not actually addressing the main bottlenecks of language models there. Sure, you're making them spiking, you're adding sparsity to something, but you're not addressing that that quadratic memory explosion of self-attention. So I find that line of work to be, maybe it's giving us insight as to what types of architectures are and are not tolerant to spikes, but I do find it to miss the mark on what is actually productive. State-space models, on the other hand, they address that memory bottleneck. They work. We know they work. We've seen industry adopt them in hybrid architectures. QN Next, for example, I would say that QN is amongst top 1, top 2 open source language models out there at the moment. So it's always fighting for that #1 spot, and it does a really good job. That team 3 months ago released QN Next, which is a hybrid architecture where only 10 to 20% of the model is based on transformer layers. So that kind of thing does work really effectively. In injecting spikes into that, I think that that's just a matter of injecting creative ways to adapt either fine-grained sparsity or interesting creative ways of information encoding. I think the community's done a pretty good job of finding good ways to elicit weight and activation sparsity. We are perhaps further behind on coming up with good ways of how to compress information effectively with spikes, but we don't know how to actually optimize models using those compression theories. I think that there is a lot of really solid work that could be done there that people want to execute. It just takes a lot of resources. We need to be able to, as a community, I don't know, get on those money bags of GPUs to be able to actually test some of these things out before we can deploy. The follow, what was the follow-up question? It was, is Hugging Face the right place to run these? This is quite nuanced because let me answer it from the view of state space models, and you can generalize it to spiking neural nets that may or may not be sparse. The state space models, the OG first generation of state space models did what I'll call element-wise linear recurrence, much like a spiking neural network. Every neuron is influencing only itself in the hidden state. That worked great. It didn't utilize as much memory on GPUs and whatnot, so that was nice. But then people realized that you've got GPUs with a ton of VRAM. and that first generation of state space models were underutilizing all the memory available on your VRAM. So what did they do? They avoided the vector recurrence, element-wise linear recurrence, and then generation 2 basically projected it back out into a matrix. So your hidden states were now represented in a matrix. People said, okay, that works a little bit better. And we're also able to fully utilize our GPUs. We're already throwing power at GPUs. So let's just use it, right? And then generation 3 just took that to another level where you've got a few more matrices that you're operating on. So the trajectory has still unfortunately fallen into the trap of the hardware lottery. That is, GPUs are the optimal hardware for a lot of the basic deep learning workloads. That's what's accessible. So let's kind of squash and mesh state space models to fit onto GPUs. Does it make sense for Hugging Face? In that case, yes. It's just a shame because people have kind of moved away from Gen 1. When I say people, I mean the deep learning crowd has moved away from Gen 1. But it is exactly that type of Gen 1 models that work really well on architectures like Spinnaker and Loihi. So if Hugging Face was able to provide a framework for smooth deployment onto these accelerators, which are accessible to us, then wouldn't that be wonderful, right? Being able to use Jason Yick's work on benchmarking these things somewhat in a standardized way with system level metrics in there, that would be really sick. Pushing it beyond GPUs is important, though.
I love what I'm hearing. Okay. Thank you very much, Jason. I think that's it for us. Thank you for closing it off with such an exciting presentation. Pete, welcome back.
Yeah, it's good to be back. Thank you, Jason. Appreciate the insights. Okay, so made it. The end of the first Neuromorphic Working Group live stream. Lots of good content. As we told folks, it'll be on YouTube forever. We'll chop it up into some individual talks too. People don't want to speed look through the whole 3-4 hours. But no, I think it was really good. Good insights. I'm sure we'll get more call for papers for the next one. You know, we do this at the Generative EDGE AI Working Group. We do one every 6 months. That's like a 2-day long live stream. So it's a real live stream at Palooza there. But this is really good. I really appreciate everyone's contributions. And for those that are not familiar with the EDGE AI Foundation, I saw that as a comment, a question. You know, we're an educational nonprofit, 501c3, based in the U.S., but we're worldwide. We're actually the world's largest community of EDGE AI developers, tech makers, and academia. We do this to help people empower themselves with knowledge to accelerate EDGE AI from an academic as well as from a business and professional point of view. You can go to edgeaifoundation.org and learn all about us. And yeah, so just kind of lean in and engage. Really appreciate it. And Peter, we'll see you. I guess I'll see you in Nuremberg.
I'll see you in Nuremberg and then in San Diego.
And then in San Diego, yes, sir.
Wonderful. Good. Thank you very much.
All right, everybody. Take care.
Thanks, everyone.
Bye.
See you.